มืดมิดไม่มีผู้ใดจากนี้ทุกลมหายใจอยากจะใช้เดินไปพร้อมเธอโปรดจะปล่อยมือฉันได้ไหมยืนยันให้มั่นใจจะอยู่ตรงนี้ใช่ไหมอย่าจากฉันไปคนที่มองเห็นค่าความเป็นคนข้างในเธอเพิ่งเป็นดังแสงไฟที่ทำให้ยังหายใจไปได้อีกวันและเธอผู้เป็นดังแสงไฟที่ทำให้ฉันหายใจไปได้อีกวัน
ได้อยู่กับเธอแค่ตอนที่เธอคิดถึงกันเจอกันได้นะถ้าเธอต้องการแต่ไม่ใช่ทุกเวลาที่อยากเจอต้องบอกใครๆที่ถามว่าเราเป็นเพื่อนกันยังต้องเว้นระยะห่างอยู่ระหว่างฉันและเธอไม่มีสิทธิ์ห่วงไม่มีสิทธิ์หึงถ้าคิดถึงก็ได้แค่นั้นไม่มีคำนิยามว่าฉันรักเธอสถานะคืออะไรแค่ใกล้เคียงคำว่าคนรักแต่เรียกที่รักก็ไม่ได้เกิดความสัมพันธ์ที่คล้ายคำว่ารักแค่เส้นบางๆที่ฉันไม่เคยจะข้ามมันได้เลยเป็นได้แค่คนใกล้ๆเธอแต่ไม่สามารถเรียกว่าคนรักจะมีสักวันบ้างหรือเปล่าวันหนึ่งที่เธอให้ฉันแบบคนที่รักกันหรือไม่มีวันนั้นอยู่ที่บอกหน่อยได้ไหมว่าสำหรับเธอฉันเป็นใครคงจะไม่ยากเกินไปมีแค่เพียงเรื่องเดียวที่อยากขออยากเก็บฉันไว้แต่คิดว่าฉันไม่ดีพออยากให้ฉันนั้นต้องทนรอยังไม่มีวันนั้นเลยไม่มีสิทธิ์ห่วงไม่มีสิทธิ์หึงถ้าคิดถึงก็ได้แค่นั้นไม่มีคำนิยามว่าฉันรักเธอสถานะคืออะไรแค่ใกล้เคียงคำว่าคนรักแต่เรียกที่รักก็ไม่ได้แค่ความสัมพันธ์ที่คล้ายคำว่ารักแค่เส้นบางๆที่ฉันไม่เคยจะข้ามมันได้เลยเป็นได้แค่คนใกล้ๆเธอแต่ไม่สามารถเรียกว่าคนรักจะมีสักวันบ้างหรือเปล่าวันหนึ่งที่เธอให้ฉันแบบคนที่รักกันหรือไม่มีวันนั้นอยู่ที่เส้นบางๆที่ฉันไม่เคยจะข้ามมันได้เลยเป็นได้แค่คนใกล้ๆเธอแต่ไม่ ธอพูดมันไม่จริงเลยสักคำแต่ว่าเธอก็ยังขอให้ฉันรอมันจะต้องมีวันของเราในสักวันแต่บางทีมันก็นานจนเริ่มท้อที่เธอบอกว่ารักกันมันเคยจริงบ้างไหมที่หลอกฉันไปวันนั้นเธอมีความสุขไหมให้เธอกอดอยู่ด้วยกันแต่ใจเธออยู่ไหนหากว่าฉันไม่สำคัญปล่อยฉันไปได้ไหมมาหลอกกันให้ยากเลยว่าเธอรักกันทั้งที่ฉันนั้นไม่เคยมีความหมายอย่ามาทำให้ฉันรักเธอมากกว่านี้เลยทั้งที่เธอก็มีเขาเต็มหัวใจอย่าเอาความเหงาเข้ามาบงการหัวใจเธอเลยจะบอกทำไมว่าเธอรักจะบอกทำไมว่าเธอคิดทั้งที่เธอไม่เคยรักไม่เคยจะใกล้กันสักนิดเธอหลอกฉันเพื่ออะไรไม่เข้าใจที่บอกฉันนั้นมันเคยจริงบ้างไหมโอเคฉันพอเข้าใจเธอมีเขาฉันก็คงต้องไปแต่จะรั้งเอาไว้เพื่ออะไรเมื่อสุดท้ายเธอก็คงต้องไปคำพูดตั้งมากมายแต่ความหมายมันเท่าเดิมปล่อยฉันไปเถอะเธอปล่อยให้ฉันได้เลือกเดินที่เธอบอกว่ารักกันมันเคยจริงบ้างไหมที่หลอกฉันไปวันเธอมีความสุขไหมให้เธอกอดอยู่ด้วยกันแต่ใจเธออยู่ไหนหากว่าฉันไม่สำคัญปล่อยฉันไปได้ไหมอย่ามาหลอกกันให้ยากเลยว่าเธอรักกันทั้งที่ฉันนั้นไม่เคยมีความหมายอย่ามาทำให้ฉันรักเธอมากกว่านี้เลยทั้งที่เธอก็มีเขาเต็มหัวใจอย่าเอาความเหงาเข้ามาบงการหัวใจเธอเลยอย่ามาหลอกกันให้ยากเลยว่าเธอรักกันทั้งที่ฉันนั้นไม่เคยมีความหมายอย่ามาทำให้ฉันรักเธอมากกว่านี้เลยทั้งที่เธอก็มีเขาเต็มหัวใจอย่ามาหลอกกันให้ยากเลยว่าเธอรักกันทั้งที่ฉันนั้นไม่เคยมีความหมายอย่ามาทำให้ฉันรักเธอมากกว่านี้เลยทั้งที่เธอก็มีเขาเต็มหัวใจอย่าเอาความเหงาเข้ามาบงการหัวใจเธอเลยหัวใจเธอเลย
อยู่ด้วยไหมต้องการเพื่อนสักคนอยู่ข้างๆไหมยินดีนะถ้าเธออยากจะระบายฉันบอกว่าคิดถึงใครคนที่เธอหวังว่าเขาจะเดินกลับมาเข้าใจนะคนยังรักมากมายมันก็ลืมช้าเวลาทุกโมงยามอยู่กับน้ำตาในใจมันยังค้างคายังหลับตาเห็นทุกภาพมันหวานอย่างนี้ ฉันเห็นเธอหวังฉันก็หวังให้มันจริงสักทีแต่เธอจะรอเธอไม่ท้อเธอว่าดีก็ดีถ้าฉันจะขอฉันก็ขอเธอแค่นี้ถ้าหากว่าเขาไม่กลับมาถ้าถึงเวลายอมแพ้ฉันขอเป็นคนดูแลเธอจะได้ไหมถ้าหากว่าเขาไม่กลับมาแต่เธอเริ่มท้อใจจะรอให้เธอนั้นยอมสักวันที่เธอนั้นพร้อมให้ฉันเข้าไปถ้าเป็นเขาฉันคงไม่ทิ้งเธออยู่กับความเหงา อเธอแค่นี้โอ้โอ้ถ้าหากว่าเขาไม่กลับมาถ้าถึงเวลายอมแพ้ฉันขอเป็นคนดูแลเธอจะได้ไหมถ้าหากว่าเขาไม่กลับมาถ้าเธอเริ่มท้อใจจะรอให้เธอนั้นยอมสักวันที่เธอนั้นพร้อมให้ฉันเข้าไปวันใดเขาหวนขึ้นมาอย่าห่วงฉันพร้อมลาเสมอถ้าเพียงเธอต้องการให้ฉันไปถ้าหากว่าเขาไม่กลับมาถ้าถึงเวลายอมแพ้ฉันขอเป็นคนดูแลเธอจะได้ไหมถ้าหากว่าเขาไม่กลับมาถ้าเธอรอไม่ไหวคงมีสักวันที่ยอมสักวันที่เธอนั้นพร้อมให้ฉันทำใจใจของฉันตั้งแต่วันที่ได้พบเธอก็พร้อมจะหยุดตรงนี้เพื่อเธอคนเดียวเป็นมากกว่ารักถึงเสียใจไม่กลัวไม่เกี่ยวแค่ได้รักเพียงสิ่งเดียวก็พอใจถ้าวันพรุ่งนี้ฉันไม่มีเธออยู่ก็ไม่รู้ว่าฉันจะอยู่ได้อย่างไรเพราะเธอมีแค่คนเดียวฉันจึงเสียเธอไม่ได้ที่ฉันหึงฉันห่วงรู้ไหมก็เพราะฉันรักเธอขอเธออย่าเพิ่งรำคาญจะฉันอยากเจออยากพบเธอหมดใจของฉันยกให้เธอเสมอยกให้เธอตั้งแต่ต้นเลย เ ใช่ไหมและนิสัยก็เป็นยังไงต่างกับฉันเหลือเกินทุกอย่างรู้ว่ามันไม่เคยสว่างภาพที่เธอแยกไปก็เพราะฉันนั้นยังฟังอยู่จนในวันเก่าๆของหัวใจสมองฉันแม้เจียมจะใกล้ตายก็ยังคงเตือนไว้อย่าห่วงเธอแต่กลับเป็นใจฉันเองที่มันไม่ยอมจะปล่อยมือกลับเป็นใจฉันเองใจไม่ยอมจะปล่อยเธอให้หลุดลอยไปตัดพอตัวเองเสมอกับเรื่องเดิมๆอย่างนั้นที่ผ่านมาแล้วฉันคือความสุขแต่ของฉันก็แค่ความสุขเก่าอันเดิมของเธอก็เพราะฉันนั้นยังฝันอยู่จนในวันเก่าๆของหัวใจสมองฉันแม้เจียนจะใกล้ตายก็ยังคงเตือนไว้อย่าห่วงเธอแต่กลับเป็นใจฉันเองที่มันไม่ยอมจะปล่อยมือกลับเป็นใจฉันเองใจไม่ยอมจะปล่อยเธอกลับเป็นใจฉันเองที่มันไม่ยอมจะปล่อยมือกลับเป็นใจฉันเองพ่ายแพ้ความอ่อนแอไม่อดทนและนี่คือคนเหตุผลไม่มีในใจฉันหรอกอิจฉาเกินไปจะลืมที่บอกว่าเธอกับฉันมันคนละทางหัวกับครั้งมันเส้นบางๆบางๆเท่านั้นบางๆเท่า
to the industry and model automotive production technology, as well as promoting academic cooperation at the graduate level between countries in the future. ก่อนที่จะเข้าสู่ช่วงพิธีการนี้นะคะดิฉันขออนุญาตผู้เข้าอบรมทุกท่านแนะนำกิจกรรมต่างๆของการอบรมเชิงปฏิบัติการประจำวันนี้ก่อนนะคะโดยการกิจกรรมของวันนี้นะคะจะถูกแบ่งออกเป็น2กิจกรรมค่ะกิจกรรมแรกนะคะจะเป็นการบรรยายหัวข้อ International Research and Educational Cooperation between RMUTK and the Thai Swedish Chamber of Commerce และกิจกรรมที่2นะคะจะเป็นการบรรยายปฏิบัติการระบบการผลิตอัจฉริยะ Manufacturing Process for eDrive Components และปฏิบัติการผลิตยานยนต์สมัยใหม่ Modern EV Automotive Industry ค่ะโดยเราได้รับเกียรติจากวิทยากรผู้เชี่ยวชาญเฉพาะด้านภายนอกจากประเทศสวีเดนทั้ง3ท่านค่ะ Before entering the important ceremony, I would like to ask all participants to introduce various activities for today. It was divided into 2 parts. The first one is the lecture on international research and educational cooperation between RMUTK and the Thai Swedish Chamber of Commerce. And after that, the second activity will be conducted. It's about the implementation of manufacturing processes for eDrive components and modern EV automotive industry manufacturing practices, which receive honor from 3 external experts. Mr. Peter Björk, President of Thai Swedish Chamber of Commerce, Professor Dr. Ken Salomonsen, University of Herved, Sweden, and Professor Dr. Roy Andersson, Jönköping University, Sweden ลำดับต่อไปค่ะขออนุญาตนำทุกท่านเข้าสู่ช่วงพิธีการเลยนะคะอันดับแรกขอเรียนเชิญท่านรองศาสตราจารย์ดร.พิชัยจันมณีอธิการบดีมหาวิทยาลัยเทคโนโลยีราชมงคลกรุงเทพขึ้นสู่เวทีเพื่อรับการกล่าวรายงานและกล่าวเปิดโครงการและขอเรียนเชิญท่านผู้ช่วยศาสตราจารย์ดร.ฤทธิชัยเผ่าเนียมอาจารย์ประจำสาขาวิชาวิศวกรรมอุตสาหการหัวหน้าโครงการร่วมกับศาสตราจารย์ดร.กมลพงษ์แจ่มกมลกล่าวรายงานต่อประธานในพิธีค่ะขอเรียนเชิญค่ะ
กับเรียนท่านประธานในพิธีวิทยากรคณาจารย์และผู้เข้าร่วมอบรมทุกท่านกับผมผู้ช่วยศาสตราจารย์ดร.ฤทธิชัยเผ่าเนียมในนามหัวหน้าโครงการอบรมเชิงปฏิบัติการระดับบัณฑิตศึกษาหัวข้อความท้าทายไทยก้าวกระโดดสู่ผู้นำระบบการผลิต eDrive Components and Manufacturing Resilience ขอรายงานสรุปความเป็นมาและวัตถุประสงค์ในการจัดงานพอสังเขปดังนี้จากนโยบายของรัฐบาลในการพัฒนาประเทศเข้าสู่ Thailand 4.0 โดยมุ่งเน้นผลักดันการปฏิรูปอุตสาหกรรมเข้าสู่ Industrial 4.0 ซึ่งแนวคิดเป็นการบูรณาการเทคโนโลยีดิจิตอลร่วมกับระบบการผลิตอัตโนมัติและเครือข่ายสารสนเทศเพื่อเพิ่มศักยภาพการผลิตการบริการและความสามารถในการแข่งขันของธุรกิจทั้งในและต่างประเทศปัจจุบันรัฐบาลได้ประกาศนโยบายดิจิทัลเพื่อเศรษฐกิจและสังคมรองรับการพัฒนากลุ่มอุตสาหกรรมเป้าหมายใหม่หรือ New S-Curve ขึ้นซึ่งหนึ่งในนโยบายที่สำคัญคือการตั้งเป้าให้ไทยเป็นศูนย์กลางในการลงทุนอุตสาหกรรมก้าวหน้าที่ใช้เทคโนโลยีขั้นสูงโดยเฉพาะอุตสาหกรรมผลิตยานยนต์และอัจฉริยะอุตสาหกรรมไฟฟ้ารถยนต์ไฟฟ้าสมัยใหม่อย่างไรก็ตามเทคโนโลยีดังกล่าวเป็นสิ่งที่ใหม่สำหรับประเทศไทยและมีความจำเป็นอย่างยิ่งต่อการพัฒนาบุคลากรรวมทั้งเพิ่มศักยภาพการแข่งขันเชิงพาณิชย์พร้อมทั้งผลิตกำลังคนสมรรถนะสูงด้านยานยนต์ไฟฟ้าส่งเสริมและสนับสนุนและยกระดับผู้เรียนให้เกิดทักษะตรงตามความสามารถเพื่อเตรียมกำลังคนให้พร้อมสู่อุตสาหกรรมใหม่ดังนั้น หน่วยงานระดับบัณฑิตศึกษาคณะวิศวกรรมศาสตร์มหาวิทยาลัยเทคโนโลยีราชมงคลกรุงเทพได้แลงเห็นถึงความสำคัญด้านการผลิตอัจฉริยะระบบอัจฉริยะและยานยนต์ไฟฟ้าสมัยใหม่และมีแนวคิดดำเนินการเชิงบูรณาการสำหรับพัฒนาหลักสูตรปริญญาโทวิศวกรรมศาสตร์มหาบัณฑิตและปริญญาเอกวิศวกรรมดุษฎีบัณฑิตโดยได้จัดโครงการอบรมนี้ในหัวข้อความท้าทายของประเทศไทยก้าวกระโดดสู่ผู้นำระบบการผลิต e-drive component and manufacturing resilience ร่วมกับนะครับทางวิชาการกับผู้เชี่ยวชาญจากประเทศสวีเดนในครั้งนี้เพื่อส่งเสริมให้นักศึกษาให้ก้าวทันเทคโนโลยีและตอบสนองความต้องการของอุตสาหกรรมสมัยใหม่เพื่อสอดคล้องการปฏิรูปและรองรับอุตสาหกรรม Thailand 4.0 ต่อไปครับในที่นี้ผมขอกล่าวเป็นเข้าสู่เป็นภาษาอังกฤษนะครับ This seminar was behold to accept the government policies to develop the country into Thailand's 4.0 by aiming to make Thailand to be investment center for advanced industrial that use advanced technologies, especially in the intelligent automotive manufacturing and electric vehicles. Therefore, the faculties of engineering has an integrated concept to develop master and doctoral programs by cooperated with experts from the University of Sweden to encourage students to keep up with the modern technologies as well as promoting academic cooperation at the education levels บัดนี้ได้เวลาอันสมควรแล้วจึงขอเรียนเชิญท่านประธานรองศาสตราจารย์ดร.พิชัยจันมณีท่านอธิการบดีมหาวิทยาลัยเทคโนโลยีราชมงคลกรุงเทพได้กล่าวเปิดโครงการอบรมเชิงปฏิบัติการระดับบัณฑิตศึกษาในหัวข้อความท้าทายของประเทศไทยก้าวสู่ระบบการผลิตอัจฉริยะขอกราบเรียนเชิญครับ
ครับขอบคุณครับก็ก่อนอื่นก็ขอสวัสดีทุกท่านนะครับเรียนท่านวิทยากรและก็ผู้เข้าอบรมทุกท่านนะครับตลอดท่านที่รับชมรับฟังอยู่ทางออนไลน์นะครับก็วันนี้ก็เป็นอีกวันหนึ่งที่ได้มีโอกาสนะครับมาเป็นส่วนหนึ่งของโครงการดีๆแบบนี้ในแวดวงวิศวกรรมนะผมในนามของผู้บริหารก็มีความยินดีเป็นอย่างยิ่งที่ได้มีโอกาสมาเป็นประธานในการเปิดโครงการตามที่ท่านผู้ช่วยศาสตราจารย์ดร.ฤทธิชัยเผ่าเนียมได้รายงานแจ้งเป็นการเบื้องต้นก็ถือว่าเป็นการยกระดับในการพัฒนาทักษะของบุคลากรของประเทศชาตินะครับให้ก้าวไปสู่อีกขั้นหนึ่งพอดูจากหัวข้อแล้วเนี่ยเป็นหัวข้อที่น่าสนใจเป็นการอบรมเชิงปฏิบัติการเพื่อเป็นการยกระดับนะครับสร้างความท้าทายให้กับประเทศไทยในการก้าวกระโดดสู่ผู้ผลิตนะครับdrive นะครับ e-drive นะครับ component และก็การผลิตที่ให้ความยืดหยุ่นในกระบวนการสร้างชิ้นส่วนทางด้านยานยนต์ไฟฟ้านะครับที่เราเรียกว่า EV drive นั่นเองนะครับก็ขอขอบคุณทีมงานนะครับที่จัดโครงการดีๆแบบนี้เกิดขึ้นนะครับผมก็หวังเป็นอย่างยิ่งว่าโครงการเช่นนี้จะนำไปสู่การยกระดับในการพัฒนาโครงการอื่นๆเช่นตามที่ท่านต้องการนะครับก็ท้ายนี้ก็อยากจะให้โครงการนี้บรรลุวัตถุประสงค์นะครับไปได้ด้วยดีนะครับก็ในเซกชันของภาคภาษาไทยนะครับสิ่งที่สำคัญก็คือภาคภาษาอังกฤษนะครับก็ขอบคุณนะครับทุกท่านนะครับที่ช่วยประสานงานกันให้การทำงานในวันนี้สำเร็จลุล่วงไปได้ด้วยดีนะครับ Vice President from the University of Sweden and Professor Ken, Professor Loy, and Mr. Peter, and distinguished guests and ladies and gentlemen. So it is my great pleasure to welcome all of you to this important training workshop on the challenge of getting the jump to become Director of Production System for Thailand e-drive component and manufacturing design. At the outset, let me welcome and offer my sincere thanks to distinguished guest speaker today, and Mr. Peter Bjork, Professor Ken Solomonson, and Professor Dr. Lloyd Anderson. I also would like to exchange my warm welcome to all the participants. I am confident this will be a workshop to provide knowledge and clear guidelines on how to be part for production system leader. To become more agile, Thailand has to extend ability to create more resilient manufacturing that can stay ahead of the challenge and get the jump on new opening resilient. This fact, as it's aligned with our vision and purpose to be the excellent university of Asia in innovation and creative technology. Each guest of this workshop, we expect this workshop to provide knowledge and clear guidelines on how to be part production system leader. I wish all of you great success in this workshop and the work ahead. Thank you. วันนี้ถึงเวลาสมควรแล้วผมขอเปิดโครงการอบรมสัมมนาระดับบัณฑิตศึกษาหัวข้อความท้าทายประเทศไทยก้าวกระโดดสู่ผู้นำการผลิต e-drive component and manufacturing resilient ณ บัดนี้ขอบคุณครับ Thank you very much
ค่ะในลำดับต่อไปนะคะขอเรียนเชิญท่านประธานแล้วก็วิทยากรค่ะร่วมบันทึกภาพร่วมกันบนเวทีค่ะ Next I would like to invite the president and our speaker to take a photo together on the stage. Please welcome. ค่ะแล้วก็ขอเรียนเชิญผู้เข้าอบรมทุกท่านร่วมถ่ายรูปด้วยกันเลยค่ะขอเรียนเชิญค่ะค่ะขอบพระคุณท่านรองศาสตราจารย์ดร.พิชัยจันมณีอธิการบดีค่ะที่ให้เกียรติมาเป็นประธานเปิดโครงการอบรมเชิงปฏิบัติการระดับบัณฑิตศึกษาหัวข้อความท้าทายประเทศไทยก้าวกระโดดสู่ผู้นำระบบการผลิต e-drive components และ manufacturing resilient ณ คณะวิศวกรรมศาสตร์มหาวิทยาลัยเทคโนโลยีราชมงคลกรุงเทพในครั้งนี้ค่ะลำดับถัดไปนะคะเราจะขอนำทุกท่านเข้าสู่กิจกรรมแรกในวันนี้นะคะก็คือการบรรยายหัวข้อ International Research and Educational Cooperation between RMUTK and the Thai Swedish Chamber of Commerce โดย Mr. Peter Bjork President of the Thai Thai Swedish Chamber of Commerce ขอเรียนเชิญท่านวิทยากรค่ะ Next we will take everyone to the first activity today which is the lecture on the topic International Research and Educational Cooperation between RMUTK and the Thai Swedish Chamber of Commerce by Mr. Peter Björk, President of Thai Swedish Chamber of Commerce. Please welcome Mr. Peter Björk on the stage.
Sawadee krap. Good morning. Mr. President, Dr. Pichai, Vice President from Skövde, Dr. Tessin, Dr. O, faculty members and PhD and master students. Very much good morning to you all. Nice to see you here. I would like to thank Dr. Pichai Atikan from RMUTK for arranging this seminar on EV drive components and manufacturing. I am also very pleased to have the Vice Rector from Skövde, Dr. Tessin here, and of course our two speakers for today, Professor Kent Solomonsson and Professor Roy Anderson. Very much appreciated that you all are here, coming all the way from Sweden. Sweden. We are a highly modern and innovative country in the north of Europe, with many multinational companies based on innovations. These companies are present here in Thailand, and they are members with the Thai Swedish Chamber of Commerce, Hakan Ka Thai Sweden. I will soon explain a little bit more about what we do. We also have several universities as members, some represented here today. And this is an important part of our operation. So I would like to make a short presentation of the Swedish Chamber and what we do. So thank you very much, and I hope we have a productive day together. Yes, I guess I have to operate this. Here you see part of Stockholm, beautiful city. And here you see a piece of Thailand in Sweden. King Chulalongkorn Palam he came to Sweden more than 100 years ago to visit, and there is a temple still there. In the winter you see it here. So I will not cover all these topics, but some that concern more the industrial cooperation, I will go little bit in detail. If you need to summarize in Thai, just let me know if you need to summarize in Thai language. Yeah, so the Thai Swedish Chamber is a meeting place for business and social contacts and a bridge between Thai business and you can say public sector also, and Swedish businesses. We started around 1989, more than around 35 years ago, with a Swedish king and the queen coming here to inaugurate our chamber. And then we have a development since. Our mission is to promote and connect Swedish businesses in Thailand. And this picture is a few years back now when we have a 25 years jubilee. But it's about to identify business and trade problems and opportunities, of course, and also provide business opportunities for our members. And we work closely with other associations and trade organizations. Yeah, we arrange different kind of social. This is the board, and we have Dr. Roy here and me, of course, on the board, and a mix of companies. Here, maybe I can say a few words. Here are some of our members. I have another slide, and you may recognize some of the Swedish multinationals here. Anyone you can, any brand you recognize? What is this? IKEA. I'm sure many of you have been there. We have 2 stores in Bangkok, coming a 3rd one this year. But of course we have one company here, Autoliv, you may not know, but they are in the safety, car safety business, seat belts and airbags and so on. And then of course, Volvo, I'm sure you know Volvo. I think they will talk about Volvo later. Saab, it's not a car anymore. Rot Saab, ไม่มีแล้วครับ Pit. But we have aerospace business in Saab and jet fighter, for example. Thailand have Saab jet fighter, Gripen. Yeah, and some other companies. Ericsson up there is the oldest Swedish company in Thailand. 120 ปีแล้ว Okay, Ericsson. Today, they work with a 5G system. ไม่มีโทรศัพท์มือถือผิดแล้วแต่ว่ามี system 5G, for example. Pointer, thank you. อันนี้ใช่ไหม This one. Okay, good. Yeah, and then, yeah, and some other companies here. Tetra Pak is a big global company in the protection of liquid. And here you will see some of the universities like KTH from Stockholm. I'm not sure. Jönköping, we're on another slide maybe. I can't see them here. Scania is an industrial company, of course. Scania make trucks and buses. So you see here that we have some of the very big companies, but also some Thai organizations like hospitals and hotels. We have about 100 members today. So this is an important foundation for the exchange between Sweden and Thailand. And the universities represented here today are important to us because we believe that with education we can develop our relationships and also the transfer of knowledge between our countries. We will hear more about that later, but we are a very advanced in technology and innovation, as I mentioned. And we hope that through this cooperation we can help Thailand and also at the same time get experiences from the industry in Thailand to our students and professors. Because your president mentioned Thailand 4.0 is important to drive now the development of the country. And you have a very vital and big automotive industry that is now about to be transferred into the EV, the electric vehicles. So this is a chance for Thailand and Sweden to further cooperate in this area. We of course, we cooperate with our embassy, and the ambassador in the middle, he was here 2 weeks ago with me to visit your president. Yeah, okay. Yeah, the ambassador in the middle. Yeah, together we do this climate survey every second year. And you can say that when the last time this was done, the result of this was, so in middle, because it was, I think, just before COVID or during COVID. But some of the advantages with Thailand for Swedish companies are safety, suppliers and service, supplier networks in Thailand, for example, in the automotive industry, and also the distributors. You have a lot of distributors in various sectors all over the country. Some of the challenges are customs procedure, customs duties, and regulations, what we call red tape. So there is always things to improve, of course. And we will try to assist in this process. Some of the important part we do is advocacy, and here a meeting with the Prime Minister of Thailand, General Prayut. He is Prime Minister at least another few weeks until the election. Yeah, I was in the, you may not see it, doesn't matter, I'm here. It was a meeting with the Prime Minister in the Thamgiap Rataban earlier last year. So this is something we do in the chamber. Yeah, so this is very important, a platform for exchange of knowledge. So we organize different networking events. Here is with the Amata Corporation. You know Kunvikram Kromadit. Amata is a well-known person in Thailand and important industrial estates as well, under the Amata brand. Some of the Swedish companies on the eastern seaboard, like Autoliv, they are in the Amata Nakhon industrial estates. I think you know about that. I think Autoliv, Swedish seatbelt producer, they have around 6,000 employees in the Amata in different factories. Yeah, this is Kunvikram Kromadit in the middle there. These kind of connections are important in Thailand, as you know. We are guests here and we need to get to know the decision makers. Here is a picture from Autoliv that I just talked about. And they have a very interesting production in Amata, mainly of seat belts. but the company is Swedish and they do also airbags and all the safety equipment. I think now they more and more advanced, and it will go to a new era about automotive safety. This is a visit to IKEA, and they are, of course, as they are Swedish, we are very keen on the environmental issues like biocircular economy. So IKEA is a good example. They have a circular shop, second-hand furniture. This is IKEA, not in Bang Na, but in the other. Yeah, during COVID, we have to develop, of course, through Zoom and Teams, virtual events. I'm sure you know that we have to cancel a lot of physical events, same as in the university. Yeah, these are examples from the virtual events with the Swedish Minister of Foreign Trade here down to the left. Here is about education. So, as I mentioned, our chamber more and more come into the area of education, and not only student exchange, but also cooperation between universities, research, teacher exchange, etc. Every year there is something we call Swedish Education and Career Days, and we used to have a monter or like a square at the exhibition organized by, I think it's GARPO or the UCSC. And many students from Thailand have been to Sweden to study. Palinyato mostly, but also a few PhD students and some bachelor students. Most programs are available in English language in Sweden, especially on the master level. So if you are interested, maybe there is an opportunity. Yeah, we do some publications, of course, as a chamber. And sustainability, I mentioned, is one of the key areas for Sweden. So Thailand is a little bit behind, but now starting to focus also on sustainable solutions for the industry and the society and at large. And here I think Sweden can assist you with solutions, technical and other solutions. And EV, of course, electric vehicles is part of the sustainability to reduce the CO2 in the atmosphere. Yeah, we have events every month, and you can join us if you want. We can exchange email and things like that later. This means Kapun Makap. It's thank you so much. Tack så mycket. Yes, if you have questions or comments, you can ask questions in Thai. ภาษาไทยก็ได้ครับ เพราะว่า we can translate Do you have any questions on in regards to Håkan Thai Sweden? You can also talk to me or our guests later during the day. I know it's not easy to ask questions in the big audience. Welcome anytime to talk to me or Dr. Roy, Dr. Kent, Dr. Tessin. We are here to help you and to be open for any questions or ideas. If you want to learn more about Thai Swedish Chamber of Commerce, you have the QR code here, or you can get my business card. I have enough for everyone, so you can log in and check out. Okay. If no further comments, I will stop there. Thank you very much. Kapomakap.
ค่ะ thank you นะคะ for Mr. Peters นะคะ ก็ Mr. นะคะท่านก็ได้พูดถึงเกี่ยวกับหอการค้าเนาะของ Sweden Chamber of Commerce นะคะว่าบทบาทของ Chamber of Commerce ที่เนี่ยนะคะเขามีความสำคัญในเรื่องไหนบ้างหลักๆแล้วก็จะเป็นเรื่องของการทำธุรกิจต่างๆนะคะในประเทศไทยเนาะแล้วก็วัตถุประสงค์ที่เขามาในวันนี้นะคะเพื่อมาพัฒนาความร่วมมือระหว่างอุตสาหกรรมไทยกับทางประเทศสวีเดนค่ะเพื่อตอบรับแล้วก็สอดคล้องกับนโยบายของภาครัฐ 4.0 นะคะซึ่งในครั้งนี้นะคะทางสปีกเกอร์ของเราเนี่ยก็ได้มีการได้โชว์การดำเนินการต่างๆนะคะที่ทางสวีเดนได้ร่วมมือกับภาคส่วนต่างๆของประเทศไทยไม่ว่าจะเป็นอุตสาหกรรมอมตะนครหรือของอีเกียก็ตามนะคะรวมทั้งมหาวิทยาลัยต่างๆนะคะนอกจากความร่วมมือทางด้านอุตสาหกรรมของสวีเดนกับประเทศไทยแล้วนะคะการมาครั้งนี้เขายังเน้นในเรื่องของการทำวิจัยนะคะแล้วก็การศึกษาทางด้านระดับปริญญาโทแล้วก็ปริญญาเอกกับมหาวิทยาลัยชั้นนำต่างๆทั่วโลกนั่นเองค่ะต่อเลยค่ะแต่ว่าเมื่อสักครู่นะคะท่านก็น่ารักมากเลยนะคะบอกว่าถ้าเกิดว่าผู้เข้าอบรมท่านไหนมีคำถามก็สามารถถามส่วนตัวกับท่านได้เลยนะคะโอเคค่ะลำดับต่อไปนะคะเป็นการบรรยายในหัวข้อ Manufacturing Processes for e-drive Components and Modern EV Automotive Industry ค่ะโดย Professor Dr. Ken Salomonson Head of Research Virtual Manufacturing Processes นะคะจาก School of Engineering Science University of Herved Sweden ค่ะNext, we will move a lecture on the topic Manufacturing Processes for e-drive Components and Modern EV Automotive Industry by Professor Dr. Ken Salomonson, Head of Research Visual Manufacturing Processes from School of Engineering Science University of Herved Sweden. Please welcome Dr. Salomonson on the stage.
ขอบคุณครับขอบคุณครับสวัสดีครับทุกคนยินดีที่ได้รู้จักครับผมพูดอังกฤษโอเคได้ไหมครับโอเค In history we will go through a journey of electrical car and electrical vehicles and how electrical motors are created. First electric car is all the way back in 1831. It's 190 years ago. 190 ปีแล้วครับ Then something happened. You see, we have 190 years ago move up rechargeable battery. Here, 1880, also a very long time ago. 150 ปีแล้ว rechargeable batteries. Then what happened over 150 years? Only in past 20 years, we see very increase in battery manufacturing for cars. It's okay, sound is okay. It's okay, yeah. We see a rapid increase only last 20 years. So why is that? Laser. Here. So only last 20 years we see rapid increase. Why is that? It's because of the substances in battery, because you need to maintain electricity. Even if you have rechargeable battery 150 years ago, they cannot keep current in battery. Cannot keep, so it can only go very short distance. So we will see that later in presentation, but here this past year a lot has gone into keeping energy in battery systems because they degrade. We will talk about substances like lithium, for example, lithium ion that degrade over time. Another point we want to make, or I want to make, is the development of electrical vehicle is pushed from governmental institution, especially in Europe. We see ban of internal combustion engine. So no combustion engine is allowed in Germany. 100% ban. So cannot drive, cannot produce. Same here in France and Great Britain. They ban in 2040. And this is only 7 years away. They will ban. So how can we do that? That means a lot of research go into vehicle production, battery production nowadays. A lot. In Europe, in Asia, and US, a lot of research on battery, especially battery and the new combustion engine. In fact, I was, today is Tuesday, right? So yesterday I was meeting with Aurobay and Volvo Car, talk about next generation electric motor. Very interesting, but I cannot tell you because secret. Volvo will have it secret, but there are new things coming. So a lot is happening. I also want to talk about definition of what we mean. So electromobility. We can see that it's concept of using electric powertrain technologies. That is electromobility. It means the electrical engine, it means the battery, it means the driveline, it means the motors. Powertrain technology, it's full electric vehicles and plug-in hybrid. So it's not only electrical vehicles alone, it can be hybrid also. And then when we term electric vehicle or EV, most of the time we will mean battery electrical vehicle and not hybrid. Here is one, just a sketch of a generic electrical vehicle. It constitutes from a battery pack. Between the battery pack and the electrical motor, you will have inverters, control unit to control what's in the battery is DC power, and you want to transform it into AC power so you can drive your engine. That's why you need the inverter and also the micro control units that can change rapidly. So that is it, battery, inverter, and motor. Now we break it down even further. We look on an explode view. This is actually an electric Volvo truck. Here we have the battery pack. Here is the inverter, and here is the electrical engine. These three topics, 1, 2, and 3, those are topics within my research group. I have 15 senior researchers in my group, and we work and focus our projects. First one is focus on laser welding of hairpins. These are hairpins. I will talk more about that in a little bit. It's for the stator. And then also we focus on machining of stator housing. Second component is joining process of bus bars and connector to assemble high power electronics, because it's very high power. It's 900 volts in voltage, and currents up to 30 amps, 30 ampere. So you need thick cable, and you also need to connect them. Third area that we look at is the batteries. Battery manufacturing using laser and ultrasonic welding, so that's one area. And we also focus on structural integrity and stability for noise, vibration, harshness. So this one, NVH, it stands for noise, vibration, harshness. It's vibration. You can get vibration if you have components that are made of polymer, for example, or thin component. It will sound like this. And it's bad material to use. Maybe not bad material. Maybe it's bad design also. It can be like that. Yeah. So these are focus areas in my group as for now. Now I focus on the electric motor itself. So now we break it down even further. So now we skip inverter and skip battery and only look at motor. The motor consists of a housing, these two, and then the motor housing, this one. So here you have 1, 2, and 3 components. Those 3 components are made from light alloy typically. They will be aluminum alloy, they will be aluminum magnesium alloy, or some type of light alloy. And when you produce it, when you want to manufacture, you use a technique called high pressure die casting. And high pressure die casting, you can mold these very quickly. You can fill one of these cavities in a matter of seconds. Yeah. I will talk more about this later, because you cannot use as cast product here. You need to machine also. Then we move even further inside. So inside the housing, you will have the stator. This is the first component that my research group looked at, the stator. It constitutes, we will see an explode view soon, but it constitutes of ferromagnetic lamellas. Here you have over 2,000 very thin sheets of ferromagnetic alloy. Inside, you push in copper wire, and then when you put those in there, you have to weld them together so you have a closed circuit. And these are called the hairpins, and these are the copper wires. And as you probably know, you engineers, you know that if you run a current through a ferromagnetic metal, you will generate a solenoid and a magnetic field. So the magnetic field will be in here and drive the rotor. So the rotor is inside the stator, and the rotor is also made up of lamellas of ferromagnetic alloys. So here is the research of today, 2020-2025 research topic. It's on rotor-stator combinations and different type of material. What you want to do is to use minimum power but maximum output and efficiency. That's what you want to do. And now I break it down even more. We go deeper and deeper here because it's important, I think, to get complete context of what we talk about. So now this is electric motor, but this is the stator here. Stator. Copper wires with the hairpins. And here's the lamellar structure. And you can see in the lamellas you have a little bit strange void in there. Those are punched out holes or laser machined holes. And why do they look like this? Why they look like that? It's not an exam, even though it looked like exam. You sit with table here. But why they look like that? It's because you want to control magnetic field. If you have void in there, you know magnetic field will degrade as 1/r³ in space. So if you make a small void of air, you will lose magnetic field in that area. So here you can control and guide magnetic field so you get maximum output. So a lot of analysis go to topology optimization of lamellars. Yeah. And speaking of that, how to machine, how to make these components. For the machining part, and especially cutting process, there are 5 different used cutting operations. One is shearing. So it's essentially like a pair of scissors. You shear material. One is punch. So you punch through. You have laser cutting. You have wire deposition, water jet cutting. Difference here, I am sure you know, but difference between using lasers to cut hole and water jet. What is difference? Difference is one of these methods will not generate residual stress. Residual stress comes from constraint. So if you use laser to cut out a hole, you will melt material. But if you use water, you will not melt material. You will take out material with no residual stress. So that's why you use this process sometime rather than this one. And here, this one here is a student of mine. I'm very proud of her. Bachelor student. Her name is Lama Awavda. She made an electric engine in her project on bachelor level, all by herself, everything, from idea to finish electric motor. What she did was she looked at the lamellas for the rotor, and she wanted to optimize shape and optimize efficiency and make it better, that engine she was working on. So she took a real engine that exists, and then she made changes to it and optimize. And she could increase efficiency by 92%. 92% better engine. Very impressive work. So this one is a permanent magnet solenoid motor. It can be an interior or a surface. Spoke shape, if we look at the interior one, this is the interior. You have spoke shape, U-shape, V-shape, and then you have surface mounted. So surface mounted will be on the outskirts instead. So that is what drives the rotor, right? Here we see some advantages. Surface mounted, it's lower cost. Because lower cost, when you do it externally, you can use other type of machining. Like, for example, if you have a stack of lamellas and you want to make tracks in it, you can use a machining method called power skiving to shave off and make longitudinal tracks in it, fairly simple. But for interior, here you need to make each lamella, you need to cut into the specific track that you want. Like this U-shaped one, for example, it comes from this U here, U, and here you have the V shape. Yeah. But it's a complex design and it takes some time to figure out, because when you make change to design, you will change magnetic field also. Here we see results from her work. She used our laser in our lab. We will see that in a little bit. But here is the external part. So this is an example of a lamella in the stator. That's in the stator. This one is in the rotor. Here is a different design: stator lamella, rotor lamella. Yeah. This gap you see in between here, you want that gap to be as small as possible, because like I said, if you have air gap and you add a magnetic field, you will lose power very quickly. So the tighter gap, the better. So then it will be more force that's transferred onto the rotor, and that means more torque in your engine. All of these lamellas, I said there are over 2,000, 2,500, 2,300, depending on thickness. But when you put them on top of each other, like a cake, it's called a stacking process. So stacking process, you can either do welding, you can bond with adhesive, or you can use rivets. So when you take all these pieces and you put them on top of each other, the welding part here is you weld on the outside of the stator, and you weld like an helix, like this, not straight. Because if you weld straight, then you will get currents in areas where you not want currents. So you want to weld like a helix, like this. Then it's better flow for a magnetic field. And when you bond with adhesive, then it's very, very thin adhesive layer. We're talking 50 to 100 micron between, and it needs to be perfectly flat, same thickness. So how can you do same thickness if you have adhesive inside? I will let you know. Inside adhesive, you put in glue, you put small glass balls, small glass beads inside adhesive that are 50, 100 micron, and when you put that in adhesive and you press it down, then you will have same thickness. And rivets, of course. Rivet you punch through. You know a rivet you punch through. Yeah. Okay. So that is about the lamellas. Now we will move to the housing and different type of machining. So now we imagine that we have created a housing. I will show you, so you follow me. Here. This one. And we want to make this surface in here, we want to make very smooth, very smooth. And what do we also want? What do we also want? We want this to be perfectly round also, perfect round. Because this stator will be inside here. So we need it to be perfectly round, otherwise we cannot push it in there. So now I will show you an example on how we work with machining of thin light alloys, thin-walled light alloys, and how to machine it. This process is called boring operation. It's an internal drilling operation. So you will machine it from the inside, and it's called boring operation. And the analysis that we did here, some of my students, Andreas, looked at how should the milling or boring workpiece, boring tool, how should it go? Where should it machine first? What track and how much can we take and still maintain round shape? Like this. So technique, I will not bore you with the equation that much, but consider your tool here. It come in and you want to machine the workpiece like this. You have different forces acting here, 2 forces, because this one is in 2D, yeah? Then you have rotational force, but you also have 4 index locations. These 4 index locations will shave off material as this one moves there. So this is feeding rate. And then you have machining velocity, and then you have depth of cut here. And then you use equations to calculate how much and try to predict. We try to predict for different type of materials. We try to predict the forces and cutting depth and try to optimize how much can we remove. Material removal rate is what we were after. We want to do is as quick as possible. Yeah, and we set up different tool diameters. You see D here, tool diameter. I go back a little bit so you see. It's this one here. Cutting depth here. Corner radius, helical angle, number of teeth on tool. And these are materials for the tools. And then we run different type of scenario in computer and also validate with experiment. And here is one example. You can see the solid lines here in red. That is the experimental value. And the numerical model that we develop is the dashed line here. Blue solid is experimental, and dashed line is our simulation model. So here we develop a simulation model so we can look at different type of scenario for different operations. And here is another example. See, solid line is experimental and dashed line is our model. And of course, you will, with experiments and simulation model, in simulation model, you not take into account all factors. So that will be challenging to do, but I think still okay. Okay. That is numerical model we have. Now we look at removal of thin layers. Because when you do thin layer removal like this, you generate a lot of heat because you shave off. It's almost like friction. You shave off very thin layers. And now we will see something here. And I want you, when we look at this movie, I want you to try and listen to sound change. I know Thai people very sensitive to sound. Okay? Different. Please look at this. You see here, stable, shatter. And different types of revolution RPM on tool. Okay, you can hear a difference in sound. So here you want to have stable process and not shatter. Shatter means you get uneven surface. So when doing machining of components, especially for eDrive, you have very, very, very tight tolerance. Here you want smooth surface. So here we see difference. One with shatter. This is what we're seeing here is this one is a stable process. This one here, shatter process. Uneven surface. And this one is a micro topographical plot. So you take a small, you magnify it basically and look at how smooth the surface is. And this is what shatter look like, and this is what the other process look like. So stable, shatter. If you do that, and you plot that in an Excel sheet, like a chart, like this. You have depth of cut here. This is what you want. You want to select something. Let's say you are a manager and you say to, I want 0.7 millimeter depth of cut. You take this row and you move here. So this value, this value, this value, and this value, those are okay, green, okay value. That means that for 0.7 cut, you have these two values. It means you should run at 10,000 RPM or 10,200 RPM with 0.7 of cut, 0.7 mm, I should say. Then you have a stable process and you will get a smooth surface. Then you look here, this one. I can choose to use 11,200 and 11,400 Kodai. Okay? But what is the difference between 10,000 and 11,000 RPM? What you do is that you actually deteriorate your tool quicker because it's higher impact. So you will have to change tool more often. Yeah? The other way around, when you reach the shatter boundary, here, you have unstable process here. So here we see that it's very important to have nice tolerances and also be very thorough when you do machining operation. I should say and mention also, this is a newly recruited associate professor in my group. He very, very good. His name is Mehdi Enyan, and he is a vibration specialist. He probably top 50 in the world actually, and he came to my group now as a vibration specialist. He worked with what's its name, in British Columbia in Canada. So he worked in a top group in machining in the world. We will see a name of his co-worker soon. Yeah. So you have different types of operations here also, but all of them will have shatter stable boundaries. So the first one I said for thin light alloys, it's the boring operation. It's what you do internally. Inside, if you want to make pipe smooth inside, you can use boring. Then you have turning operations. And here you clearly see vibration marks, and that is not that is due to process parameter. So you can tune those and get smooth surface. Here you see difference in milling operation. So milling, you go like the process we saw here. Shattered surface, stable surface, and this is what you want, not this one. Because if you get shatter, you have to do machining afterwards and polishing. Yeah. We can see that you can have different type of ship formation when you do turning operations, but depending on velocity, like I said, you can have tool fracture. So you can chip off the tool and then you have to replace tool, otherwise you will not get smooth surface. Okay, if we sum it up with this one, this is your machining structure. That is where you, that's the vise. You put your tool into the vise. The vise will have displacement, so it will vibrate, the machine will vibrate. It come into the process. So even this one here is when you turn on the machine and you hear a sound, it will vibrate at the micro level. Then you add a machining process to induce more force. And then those forces will go into cutting forces, these ones. And then this is the entire loop that you need to consider when you want to remove shattering. And here is a bigger view. It's called the load chart. Shatter, 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 and stable. So it looked like this. And this chart is actually from the movie you saw there. So you run your tool, the milling operations, at different settings, and then you measure by sound. You measure the power of the sound, record sound basically, and then you look at the frequency span, and you can see if it's stable or shattering, because it's not comfortable for ear when it's shattering. Very high pitch frequency. And you can see here it's the microphone signal intensity. Stable lobe diagram. So they can look like this. Of course, the spindle speed, if you have no speed, it will not do anything. So here is stable. But then you increase and you go up in depth of cut. You see, you will have larger regions of stability, but you also have possibility to go into deeper cuts. As you move, increase your spindle speed, it also make you able to cut more because it's more force coming into the impact, which means that you can shave off more because you put more energy into process. And for those of you who notice, it's a OPT here. That point is the optimal point for this chart. So optimal point is about 1.8 mm of cut and about 8,000 RPM, for example, for this process. So I need to have some equation because it's what I do. Yeah. And as you can see, I know cutting process, machining, is one of the most difficult things to model on the planet because there's so much going on here. You have material changing, melting, heat, friction, mechanics, you name it. Everything go into cutting. So essentially, this is just a tip of a tool. You have shear region, so that's when you shave off material. You have, this is your workpiece here, so depth of cut, cutting speed, ship formation. Sometimes you will have rakes here that will break ships, so you get smaller ships. So all of that you can add into a diagram where you record the signal of the process by a microphone. And then once you have the microphone sound, you can analyze it by the intensity of sound, and you can make your own lobe diagrams like this. This here is from a GUI that Mehdi did when he was working with, I think, #1 in the world, Altintas. He is a machining expert from British Columbia, Canada. So Mehdi, he did his postdoctoral studies there in Canada. Other types of things to consider. These ones should resemble stiffness, compliance of the machine itself. So when you put your vise or fixture, your spindle into your machine, how rigid is it, or how compliant is it? You need to tighten all bolts so it's stable and fit. Then if you do that, you will increase frequency of these springs here, and then you minimize shatter. So you will change low parameters by tightening bolts in your machine. Here is a 3D view of that sound frequency and vibration frequency. Spindle speed now on this horizontal axis. Into the board is depth of cut, and then you have frequency spans here. And here you see now the lobe diagram. Yes, lobe diagram in 3D. I have been told we need 5-minute break now. Someone tell me you need to stand up and take a break, take a little bit of break. How long? In 5 minutes. Yeah, so keep on going, 5 more minutes. Yeah, sorry about that. Okay. Here is the GUI that Mehdi developed. So it's a very nice GUI. You feed signals directly into this GUI. And what it does is that it prints out your lobe diagrams as you're doing your tests. So when you run your tests, it will add points to your diagram. So this is something that's very nice to do and develop, and very useful. It can look like this. Okay. Okay. So here is ongoing work now. So this is what he is working on now. Selection of suitable signal features. So not only sound, but also use, for example, laser triangulation, things like that. Measuring phase shifts, so you can induce different type of frequencies on your process to look for phase shifts. And different types of classification algorithms, and that is to include machine learning and AI, which is very hot topic. And here is the structuring. You take out your matrix of data, signal spectrum, decompositions, because you need to split your process into different frequency regimes. and you do a lot of filtering, and then you end up with your wavelet packages. When you use machine learning and you use classifiers, you can do supervised learning or deep learning, depending on what you have. So for this, he has chosen to use support vector machines, amongst others, just to train your network and your model. So once you have your model, then that can train itself essentially. For deep learning, here you need a lot of data, so it's time consuming. Yeah. Now, I think now is a good time for a break, because now we finish machining and now we go into laser welding now. Okay, so we take a small bapping break.
โอเคค่ะ ค่ะ เดี๋ยวต่อไปนี้นะคะ จะขอเชิญผู้เข้าอบรมทุกท่านนะคะ เบรกประมาณ 15 นาทีนะคะ สามารถรับของว่างที่ด้านหน้าได้เลยนะคะ เราจะเบรกกัน 15 นาที แล้วก็จะ continue section นี้ต่อค่ะ ขอเรียนเชิญค่ะ Yes. ค่ะขอเรียนเชิญนะคะ ผู้เข้าอบรมทุกท่านนะคะ เข้าสู่ห้องสัมมนาของเรานะคะ เพื่อที่จะ continue section ต่อกันเลยนะคะ ขอเรียนเชิญนะคะ ค่ะก่อนที่เบรกไปนะคะทางสปีกเกอร์ของเราก็ได้พูดถึงการพัฒนาของระบบรถไฟฟ้า EV นะคะแล้วเขาก็ได้พูดถึงเกี่ยวกับว่าทำไมนะคะระบบรถไฟฟ้าเนี่ยมันมีมานานแล้วทำไมในช่วง10 ปีหลังเนี่ยมันถึงได้มีการเป็นที่นิยมแล้วก็พัฒนาอย่างรวดเร็วนะคะแล้วก็ระหว่างนั้นนะคะสปีกเกอร์ของเราเนี่ยก็ได้พูดถึงระบบการผลิตรถยนต์อัจฉริยะนะคะแล้วก็องค์ประกอบต่างๆระบบทำงานต่างๆนะคะซึ่งคิดว่าเป็นข้อมูลที่เป็นประโยชน์ต่อผู้เข้าอบรมเป็นอย่างมากเลยนะคะโอเคค่ะ next นะคะ let's we move on or continue the session ค่ะ please welcome
โอเคขอบคุณครับขอบคุณครับ Okay, so now we move in to other type of construction in electrical engine, move away from machining and go into joining instead. So, and specifically laser welding. This here is our laser machine that we have at our lab in Sweden. It's a true cell laser. It's an industrial laser. Maximum power is 6,000 watts, so 6 kilowatt. It has a fairly large, because it's a fairly large working volume, because it's industrial laser. You see, you can add it into production line, so you can open up doors and you can add production line for inline laser welding of components in manufacturing. It's a solid state disc laser. It's 1030 nanometer wavelength and as low as 120 watt of power. What we have chosen with this laser, because we have very special processes in manufacturing, we have chosen to add PFO and different types of shielding gas. So this one is the PFO. This one enables us to guide the laser beam and the focal point of the laser. We will see it soon. Here you have a mirror, so the mirror will control where the laser focal point will go in specific tracks, so you not need to move your object while you laser weld. PFO, programmable focusing optics. Like I said, shielding gas, it's also very important for laser, because when you laser weld something, you can get the porosity inside, as we will see. You can get inclusion of different substances from the air we breathe. So if you not have shielding gas with a specific flow, you will get bad weld, and that's not what you want, yeah? The process that we look at, we saw earlier, I showed you earlier in the electrical engine, is that we need to put bent copper wires like these, need to push those into the lamellar ferromagnetic structure of the stator. Copper, as you know, it's a material, it's very soft, very soft. I can bend with bare hand like this, no problem at all. It's very soft alloy. Problem with this, when you push this into the lamellar structure, you can bend the copper wire. And when it come out on the other side, up here, it come out there, it will not have the same height. So the hairpins, this one come up through the lamellar structure, then another one will come from this side here. So you will have the hairpin couple there. We will see better soon. It looked like this. So here you have, for each angle, if this is the center, for each angle you will have 4 different copper wires, 2 hairpin couples that need to be welded, so you have a closed circuit. But difficult part, and this is why I chose this as a continuance from machining, because one big issue in electric engine manufacturing is to make all of these hairpin couples same height and flat. So here is a challenge. How can we do that? Is milling a good operation, or is shearing a good operation? Water jet cutting, or how should you do it? So we spent about a year and a half to look at how to make these flat. Another thing when it comes to laser manufacturing and laser welding, copper is very shiny material, very shiny. So when you cut, you will have, the laser will actually reflect on the surface and bounce away. So the energy will not go into the weld. It will go away. So if I say I put in 3000 watt onto with the laser source, only 2600 might end up into the weld, which means I use less energy to make the weld than I want from machine. So that is a problem. And to make all of these straight and flat, we need to develop also this type of fixture. So this is not the stator. This here with the pink handles and these bars and all of this here, that's a fixture that we developed to make it possible to punch it into the lamellar structure. So it will not go into, the stator is in there. This is stator and this center here, but all of this will go away. You will take that off once it's finished welding. This is what it looks like. So number of challenges here. Copper wire will come on a big roller, copper wire. Typically, the diameter of this copper wire is about 3 to 4 millimeter in 3 by 4 millimeter, 4 by 6, different type depending on engine, yeah? Once you have those, you need to have a bending machine, special bending machine that is specific for your engine. It will bend like this. Then you need to assemble it and punch it through like I showed in the previous slide, like this. When it comes out here, you need to twist it like this. Twist. Why you twist? Why twist? Because you want to use less space, less room, so you twist it and make it nice. Yeah? And then you will have it like this, and here you do laser welding. So this is 1 hairpin. And around the entire stator is over 100 hairpin welds. Okay. Before we do any welding on an actual electrical engine, we need to establish what type of laser process parameters should we use to make a good weld, depending on the alloy. The alloy that we use is close to 100% copper. It's 99.67% copper, pure copper. Yeah. But if you want to determine your laser process parameters, you can, for example, have power and number of runs. It means number of runs we will see soon, but number of runs is tracks for the laser spot to make the energy come into the weld. So in this example, this one is called a design of experiments chart. We have 15 samples. We have 15 power, 15 number of runs. So here we need to do 15 examples, yes? So we developed this small fixture here, and we just plug in couples of copper wire. And then we did laser welding on those to see how do they act and how are the hairpins, how do they look like with these process parameters. And here now we will see a weld, you see? It goes around here. Here is the laser focal point, like that. I can tell you this process here is in real time, it's 0.2 seconds long. It's like this. But here we have equipment in our lab, which is a high-speed camera, and this is footage of a high-speed camera footage of the laser weld once the copper is melting, and solidification also. You see here we have the molten copper. The laser source is turned off, and we can see that now the dendrite solidification process will start here, and it will move up here into the core and solidify the copper bead. Yeah. The settings we used for this test is 5,000 watts. We use a velocity of 500 mm per second and 11 repetitions in a circle like this with radius 3 millimeters. So it's a circle, 3 millimeter circle. Now you see it's solidifying here. Still molten in the center, but it comes in, pop, there, now it's solidified. And what we have seen here is a process in real life, 0.2 seconds, but in movie here it's 1 minute and 10 seconds. That means we can track, using image recognition software, we can track the shape of the laser mold. When it melts, we can track it. And you see it looks very nice, like this, but it's on the outside. We don't know inside yet. Now we next one here we will see. See, there you go. So now this one is now 6,000 watts, 1 meter per second, 16 laps in a circle. You see a difference here is that you have a splatter like this. It shoots away copper alloy. Because laser is just it's essentially it's a heat source, and you can it's so much energy in the heat source that it will melt the copper, and then when you run it in a circle that quick, you can actually develop turbulence inside the molten copper, and it will be like this. But please notice something here now. It will look almost exactly the same, but you have all of that splatter that will shoot material. So what will happen if you have copper shooting away at other hairpins that are very close to this one? Then you can have short circuits, you can have a bunch of electrical problems that you don't want. So even though it looks the same on the surface, we don't know if it's a bad or good weld because of this splatter. So that's why we use high-speed camera to look at it. Also, one thing I want you to notice here for reference, there is sharp edge here. Here, sharp edges. Why? Because we started the laser in the center in a circle like this, and it's so quick. So the time it takes for the heat to dissipate, to melt the edges also. It's too quick. It cannot do because it's very quick. Okay, there you go. So once we have welded, let me just see, hold on. I will do like this, yes. So once we complete the welds, and we do a lot of tests, I think we've done before this 150 tests. I just show you an example of 15, but we have 150. We need to have a look at how does the weld look like inside. So we take and cut all the samples through cross-section, just cut through, and then we want to look at the grain structure inside. And I'm sure there are lots of material scientists here. So you etch your samples. You can use different types of acids to do that, but this is what we use, hydrochloric acid. So we want to do that. We bathe the samples once cut into hydrochloric acid solutions, and then we take it out, clean it, and then we can look at it, because then the grain structure of the samples will appear, and it will look like this. So now we cut the samples. Maybe, sorry, is possible to turn off light a little bit so we get, or maybe not possible. Only here if possible. Sorry. I want you to see this because I don't think it looked clear here. Just one notch, maybe it looked better. Sorry about that. That is perfect. ขอบคุณมากๆครับ Yes. Now it gets a little bit dark and cozy. Mood sabai. Yes. So here we have now cut the samples, and you can see this is cut in the center. So here is in between the copper wires. And then up here, we see that there is a completely different grain structure. This is the virgin copper material down here with very small grains. But when you add a heat source like the laser and you melt the material, you will develop a heat treatment for the copper. So you have a different grain structure like this, very long grains, because it's molten. These ones, that one and that one, these are pores. Pores are cavities inside, they are voids, and they develop because of the turbulent flow of the molten copper. But they are enclosed, so you cannot see it on the surface because they are inside here. Here's another one. This is sample 1, so it's that one, and sample 7 is that one. We see it's a lot more flat, it's very smooth like this, but we don't know if there is a void in that one either, because we only cut in one plane. And the grain structure is a little bit different than this one. So what is difference between those two? We see we have 2000 watts for this one, 6 laps. This one increased by 1000 watt and only 4 lap. So if you calculate this one, energy is almost the same that comes into sample, because energy is power multiplied by time. That will give you the energy. So almost the same. Here is another sample. Now we look at sample 11 and 14. So sample 11 have a longer keyhole. This is keyhole depth here. Yeah. And grain, it looked very smooth like this. But what is this? that is could be a micro crack. So it comes when you cool down the sample and it solidifies. You have shrinkage inside, so it solidifies and you can develop cracks like these and small voids. 4,000 watts, 3 laps, and then sample 14, maximum power, only 2 laps, and it looked like this. Here we see that the heat radiates down into the virgin material like this, because it a lot of heat, yeah, and some voids also. Whoops. So, shape. When we look at our experimental fixture, we look at porosity, these ones. We look at shape, outside, and we also look at resistance, because major point here, when you have it in your electric engine, you want to minimize resistance because you want good conductivity of the hairpin, so you generate a good magnetic field. So what we use is this one. We also have in our lab, we have a CT scanner, a CT, an X-ray tomograph. CT is computer tomography, so we can scan and do X-rays of this entire experimental fixture and look inside each hairpin pair to look for porosities. And now, when we do that, we don't need to cut the sample. We don't need to cut. We can just look at it from outside. So we save time, we save money, we save everything. But we need to pay for CT scanner, very expensive, yes. But we can scan the samples, we can get three-dimensional view inside the hairpin, and all the voids we can measure. How many voids we have, how big are they, where are they, all of that. And we do that by CT analysis and 3D analysis. Here is another one. This one is a bad example on purpose. So this particular hairpin, it has a lot of porosities inside and very big ones, but it looked fairly okay. Exterior it looked okay, but inside it looked like this. And if you run current in this leg, you will have 30 amps of current running through one leg here. Need to go over here to the next pair. So what happens when you have a lot of void inside? You will develop called high current densities inside. And high current densities, they are local increases of current, because you have less space and less volume to run the current. So that can generate more heat, and then it can rupture under fatigue loading of like thermal fatigue and EMC fatigue. And you not want that either. Once we have done all of these tests, we also do simulation models. So we do digital twins. So this is inside computer. We run and develop laser welding models and numerical models for laser welding. So we can have a digital twin, which means that we not need to do any physical welding. We can just run different parameters inside the computer instead and look at, number one, at temperature. We look at melt region also. So melt region will determine the keyhole formations, and also how much of the hairpins do we cover with these parameters. And a laser, when you do laser welding, you always have an angle towards your sample, otherwise you can damage the laser. So typically it will be 5-degree angle like this 5-degree angle towards the sample. So any laser beam will reflect away from the laser, otherwise you can damage it. Since reason is, since you have distance from laser source to sample, that's where you have the focal point. So when it reflects and go back in, you actually have the same focal point inside the laser, so you can damage it. But we can do all of those tests inside computer also. And here is one of the simulation models for validation. As you notice, in the real sample, you have a void here, but you don't here. And reason is that that was not in this solver. When we ran this simulation, it did not include any porosity function. So once we add that to the solver, then this pore developed here. So other than that, it looks almost identical. You have the flat surface up here, this one, you have this one, it's there. So it looks virtually identical with the sample. So that means we have a good model for laser welding, and we use it and develop it every day actually. And here, this is a thesis project I had on bachelor level. They developed this model and DOE last year. And one of them is now one of my research assistants, also a good student. They also, those two students, they also looked at the image recognition possibility. So you look at shape of the hairpin. So this one is bad shape. It has sharp corner like this. This one is very smooth like this. So this one is okay. This one is not okay. It's over welded, sharp edge, no sharp edge, sharp edge, sharp edge. So if you take those images and you plug those into image data recognition software and you generate a neural network here, neural network, you can feed that back into your model and you can develop a neural network that will change laser parameters and trying to find patterns. Yes, and here, now we have done a lot of testing and now we have all the components, all the parameters we need. Now we need to fine tune it. Fine tune and actually weld on the application, which is the stator. So we chose the elliptic shape, it's this one. This is the hairpin pair, like you see, and welding path. We have a set of parameters. So this one is fine-tuned now. It's in the scope of what is good. And we have different setups here. This here is the PFO setup. So remember the PFO, instead of moving the sample, we can move the laser source by coding and mirrors. So we can move it around this track just by change of a mirror. And the software, I don't know if you can see it here now, but there's a blue line here. So it's equivalent to this line. So it will automatically find this hairpin pair, establish the midline, and then it will make a small cross in the center, and that will be the origin for this ellipsoid. And once it focused on the actual hairpin, it will send signals to the PFO, run weld, and it will run like that. And here is a setup of different type of grinding. Since you're machining and materials, you will know different type of grinding for substrate. So the final one we do is diamond polishing, so we can look at it in microscopy. And here are some of these samples now with better laser parameters. See, not too many pores in here. Only a few small ones. Nothing here. That one failed. Too low power. These ones, 1,400 watts, 2,000 watts. They not even break the surface. So that is what I mentioned, that it's important to use correct energy and not only focus on power, because energy is important. You can see a little bit different grain structures also for the different samples. Okay, sorry. In this one, here, from top down to here, that is what we called keyhole depth. So that is how much does the weld penetrate the sample. Keyhole depth for the parameters. And what we wanted to do with this so-called DOE was to generate a surrogate model or a meta model. And here you have number of runs on this axis. Here you have the power on this axis. And on the vertical axis, you have the welding depth. So that is the objective of this one. Yes, that is the objective for this one. So you can approximate a surface in here. I will show you later that surface, but it's like that. That is welding depth. Then we move into next portion, and that is resistance. We want to check for resistance also. So we created this fixture here, 3D printed, polymer 3D printed fixture, and you put the welded hairpin inside this track, and you have the hairpin bead up here. You can notice you have one hole here, one hole here. So when you have the hairpin, you add a current through it, and then you run the current through it, and you measure voltage here between 2 points. You measure voltage, and with voltage and current, you can calculate resistivity. Then you do same up here, one hole here and one hole on the other side, and you measure voltage, current, and calculate resistivity, and you use this one as a reference measure. It's kind of like this. Here is the setup. So here you have the hairpin. You clamp it down, and then we run a high power current through it, and then we punch out voltage over a specific length, voltage, specific length, and then current will run like that. So now we measure resistance for all these, like that. And in this plot, we have number of laps, we have power, and we have resistance. So what comes out is this meta model. That is the surrogate model. It's a quadratic regression. It means that we try to fit a surface that is quadratic amongst the resistance values, and we normalize it so that we can compare. And then we use what's called a priori radial basis functions to change the surface so it fit all the points. Then this will turn out. And if we do optimization on that curve, we can pinpoint exactly which parameters to use. So the minimum resistance will be on this surface here, all points within this surface, and all points within this surface. Then it's just pick any one of those, and you will have minimum resistance. That is the meta model extraction. This one is the same one as the previous slide. But the track is elliptical, is this one. If you change it to 3 lines, so 1, 2, and 3 lines, like just 3 lines instead with the laser, then you get this resistance curve. If you change it into a cross like this, you will get this surface. As it happens, you see that one, and that one, those minimas of these meta models, they coincide, which means that these are good parameters to use, irrelevant of how you run the laser. And here is some of the future work. So we will study more on porosity development and see if we need to clean it or if we need to do something with the shielding gas. We need to characterize our surfaces. We want to do and have done a little bit on fatigue, so we will run thermal fatigue on our hairpins. Those are 3 of the topics that we work on now and in my team. Okay. So, from our experimental development of experimental fixtures, of techniques, numerical modeling, all of that, we can use our knowledge, add physics-based data sets, physics-guided algorithms, and then use measurements to optimize our algorithms. And once we have all of this, we will generate very nice electrical engines, and especially when it comes to hairpin welds. And this here is, we've actually, not that picture, but we've actually done welding for next generation drivelines for Volvo. As Peter mentioned Volvo, you all know Volvo, I assume. But you heard it, yes, it's the car. But you know Polestar, you have Polestar 1, Polestar 2, Polestar 3, fully electrical Volvo cars. We have done laser welding for the latest versions of that, so it's very nice, and a lot has happened in past 2 years. Okay, now we move on. Now we finished with the engine, or finished with our research on the engine. Now we move on to inverters and power cables. So this is now in between. Here is the electrical engine, but power need to come from somewhere, and it's alternating current. AC power will come in here, otherwise it cannot move. So the inverter is what transfers DC power into AC. Then there's a control unit that will control the communication and feed the power. Yes, and you have very high voltage coming in there, so you need to convert that voltage also, because charging stations of today, they need to convert the power, so it's operational. And it looked like this: battery, inverter, and motor. The powers and voltage for plug-in hybrids, it's 300 to 450 volts. And you have power 60 to 100 kilowatt, but you can only drive 50 kilometers with that setup on electricity, I mean. But nowadays, with the battery-powered ones, you go even up to 900 volts in voltage. You have plus 150 kV, you know, Tesla's new car, for example. They're, what's it called? The super duper race car, Tesla, has over 1,000 kilowatts, and they can run 1,000 kilometers. So it's very high development on those. So that's the battery powered ones. These are some of the cables that are used. You have different type of fixtures depending on OEMs, like these. You have material combinations, copper, aluminum, aluminum, zinc, copper, etc. Different combinations and different fixtures. But how are you going to fuse these together? The preferred methods to use is laser welding and ultrasonic welding. So that is what I will talk about now. In ultrasonic welding and laser welding, it all starts with the microstructural features. Then with heat, you add mechanics. So you have 3 different items to take care of here: microstructure, heat, and mechanics. And you can follow, I will not read all of those now, but you can follow the numbering here. So if we take 1, 2, 3, and 4, it's the uppermost ones. Thermal stresses due to microstructural change. Here, microstructure. If you have a microstructure where you have inclusions, porosities, foreign substances, and you add heat to it, it will behave different than if you have another microstructure that is different. Elastic plastic behavior. I have spent almost 20 years of my research on local material behavior and microstructural characterization. And elastic plastic behavior is what makes microcracks develop, and local stresses and residual stresses. You have phase transformation, origins, volumetric changes, and phase transformations comes with the heat in either the ultrasonic weld or the laser welds. Because you add heat, you will have a phase transition of the grain structure, as we saw for the hairpins. And final 4, microstructural changes are coupled with plastic stress, because different types of grain will have different types of residual stress. And then you have all of the other ones here, and I will not go through them, but you can see how they are connected here. And also see strong, medium, and weak connections. In ultrasonic welding, it's like this. You want to weld 2 substances. So you have 1, 2 thin sheets of alloy. The start of the cycle, you start to oscillate with external pressure. You punch it down, and then you start to oscillate the head or probe. Start to oscillate back and forth. So that's friction. We all know that if you go like this, a lot of friction develop, and friction develop into heat. Like this. You add more pressure and you increase frequency. And then these 2 metals, they will fuse together. But wrongfully, many people think that they fuse depending on temperature, but they don't. It's an atomistic fuse and mechanical fuse. So it's like they do not melt, they just attach mechanically to one another, and we will see how that is later. Here is a setup of different sonotropes, different tools that you use in welding, and they are dependent on how you want your ultrasonic weld to look like. The most common one is, of course, square. You just go in with a square, and it looked like these cables we saw here, like these ones. like this one, this one. This one is a little bit thinner, like this one. All of those, yeah? So you have different types. And here we have some typical settings for different types of material combinations. Looking at aluminum in ultrasonic welding, thicknesses typically 10 micron to 2.5 millimeter. Power range of machine 2 to 3 kilowatts. Static pressure in megapascals 0.14 to 0.2. So that is when you push it together. And then welding time, 5 millisecond. Ultrasonic weld. Punch in, it finished. That was even longer than 5 milliseconds. Up to 2 seconds. And vibration amplitude is important also. So 10 to 100 micron. And I can say the frequency that you use. Now looking at this one, you know amplitude. Amplitude is peak to peak. Amplitude. It's 2A, yeah? The frequency here is about 20 kilohertz. So 20 kilohertz will fuse aluminum with these settings. And then you can look at the other ones, aluminum copper, aluminum stainless steel, magnesium, copper, aluminium, zinc. These are all material combinations for electric components and e-drive. When we look at the energy density, joules per square millimeter, as a function of welding pressure, which is this one in the center. When it says here in this graph, welding rate 0 to 70%, all of these points here, this is just an example, all of these points here fail. They do not fuse 0 to 70%, 70% fusage, whereas these ones in the middle, these clear circles, they fuse 70 to 100%. That means that 70% of the area that you intended to weld will be fused to 100, so full. And the top one here is a defective product. Maybe you punch through or something like that, or rip it apart. Here is an example, a micrograph on how it looks like after the fuse. So aluminum copper, these ones at different grades. And these are microscopic images. You see on the top surface here, little bit of wavy pattern. That is actually a pattern onto the sonoprobe that you use to make it fuse quicker, because you get more friction when it looks like that. But with the high pressure, you will deform the materials because they are very soft. And here you see possible combinations. So all the black points here, or black dots, with all the different substances, aluminum, beryllium, copper, and so on. All of those where you have black points, those are possible to fuse using ultrasonic welding. Some are used more than others, yeah. But this is a development area in e-drive, because some of these materials, can we find all of those here in Thailand, for example? Can we find all of those in Sweden, in Germany, in Brazil? No, we cannot. So which material can we use that we have a lot of here on planet Earth? Then that will be a good combination to use. Then it will be sustainable. And my friend, my good friend, will talk sustainability a little bit. Am I right, Roy? He will talk about that later. Here we zoom in a little bit more now, because I said to you that these materials will not weld. They will not, they will ultrasonically weld, but they will not melt, I should say like that. And you can see that the material structure has not melted. It just fused together mechanically, like this. Yeah. And difference is, you look here in the left corner, this is 200 joules of energy, 500 joules of energy, 1000 joule of energy, and 2000 joule of energy. And that is the energy input into the weld. And you can see, higher the energy, the more they will fuse together. So they mechanically fuse together, but they not melt because the temperature is less than 300 degrees. And as you know, copper and aluminum, they have melting points in excess of 600 degrees. So it's not possible for them to melt, but they can slurry like this. And then they fuse mechanically. Problem with this is that you can develop voids. If you have too much energy, you get voids there. And voids are initiators for crack deformation and fatigue crack. So that's not good. Ooh. Yes. So now to a little bit more fun, I think. I think all of this is fun. Here, now we look at this one. That is 1000 joule energy, copper, aluminum, and there's a scan line. So the scan line, this is a scanning electron microscope image, and the EDS, that's energy dispersive spectrometry, along this yellow line. And what does that do? That tells us which substances do we have along that line. This is start of line, it's down here. A lot of aluminum, 100% aluminum here. Now I'm here, and it's 10 micrometers in here. So when I'm up there, I have 100% copper. So this is the phase change. That's aluminum, how that looks along this line. This one is how it looks for copper. In the center, you have aluminum copper, both of them, 50-50, passive. That's how it looks. But why is it useful to know this? Because if I want to make micromechanical models of this joint, and I want to say how strong is that joint, I need to have material data. So what I do is that I take this picture, and instead I use image recognition software, and I use tools to capture the intensity of the images, and I relate the intensity of the image along that line for aluminum, for example. This is the gray value intensity starting here to here. It looks like that. Now I have that. Then I can cross-reference that with my original EDS curve, and I see, here is the intensity plot. That means that all the intensities that are on the level I have here, I can say these are aluminum. If you have this intensity, you should have aluminum. In my micromechanical finite element model, for example, it should be aluminum. And then vice versa for the copper, of course. Also, when you look at ultrasonic weld, we use the same approach here. We use X-ray tomography. We take out a sample, and this is just sample copper aluminum joint that we have ultrasonically welded, and we put those in our CT scanner. And then these different planes here, the gray planes here, are shown here. So those two are this one and this one. this one here is this one. So here I can track, and I see that inside my ultrasonic weld, I have voids in there. And it's because the tool that we used have two sharp teeth. The pattern is too sharp, so it will destroy my weld, and I don't want that. But that's just an example on how we use our CT scanner also to look inside the welds. And of course, you can also do finite element models from this and export to finite elements. Okay, now when we have ultrasonic welds, how do we want to use it? So this is the basic setup of an ultrasonic welding machine. Power supply, controllers, transducers, booster, sonotrodes, vibration, horn tips, anvils. So here is where the actual process happens. But from this one, we can extract data and measure. We can measure frequency, energy, pressure, all of it, and we can feed that into a deep learning neural network, and then we can estimate and learn as we do testing. We can train our machine learning algorithms to increase our weld quality, and we can also add more data. If we do this tracking for an inline production process, we can track the data over time, and we will have a machine learning algorithm that will be better and better. For those of you who are interested, this one is a pouch cell used in EVs also. Pouch cell battery. And pouch cells you need to ultrasonically weld because they are very thin. Speaking of batteries, now we go into batteries. Now this one here is instead, now it's a cylindrical battery cell. But what most people don't think about is that batteries for automotive companies, they get very warm. So you need to have cooling channels inside the battery. So otherwise you will have too much heat and they can burst into flames. So there are coolant running through the battery packs like this as you pack the cylindrical cells. The third component is actually, you have pouch cell, cylindrical, and then you have prismatic cells also. And in my group, we work mostly with prismatic battery cells. Forget to mention also, batteries, as you know, they are very close to the ground. And why is that? That is because it carries a lot of weight, so you want the stability of your car to maintain. So you put the batteries very low, very, very high weight. We dive into the internal structure of a battery. You have sheet metal, so you need sheet metal forming. Here you have all the different battery packs that turn into this module. So within each pack, you will have a number of different battery cells. So it's battery cell, pack, and then module. You have polymer components surrounding it, so you keep it inside and intact so it doesn't vibrate in there. You have different types of thermal reflecting foils, more polymer, and then sheet metal forming. And you pack all of that into one battery module. And here you also have some foreign substances, nickel, manganese, and cobalt. That's one type of battery, lithium, iron, phosphate, etc. And that is a problem because these substances do not exist all over the planet either. So you will have a problem with supply chain here. I will, here you have a reference for this material. why Europe can secure enough critical raw materials. So it's about sustainability and securing the material, because it will be a supply chain problem later. Here is some more information about that with different substances. Okay. Now, here is the overview, an overview of different tests you have to do for a battery when you produce batteries. All of the ones that are black, thermal cycling, salt spray, all of these, I should say those are the most important for battery manufacturing. Those are essential. Then blue ones, fire tests, altitude, those are secondary tests that you do, because altitude, of course you can check it, but you will not take your car on an airplane unless you're super rich or have some idea that you want to bring your car somewhere on the airplane. So think of all the black ones as good tests to do. So those are, when we come into our battery projects, research project on batteries, we will develop some models and some experimental fixtures for these, because they're going to build a battery plant nearby our university in Sweden. So we need to be prepared. Here I want to mention also, when it comes to batteries and battery development, this is a recent project that's up and running now in my research group, and I am principal investigator. We used multi-scale optimization, modeling techniques, and numerical method development to simulate laser welds at local scale, structural scale, but we also do multi-physics modeling. So we check chemistry, thermals, all of that, and we want to integrate everything into one numerical model. So if we say we want this configuration of our batteries, then the model will tell us you should use this type of process to develop your battery. But it's all numerical, so it's all in computer. And this is the idea. Laser welds of bus bars, so tab to bus bar. Bus bars are small metal sheets that you connect the battery cells into battery packs and then into battery modules. And we, of course, we have a lot of information, as you have seen, on development of hairpin welds. So from that, we can plug that into our numerical models. And here is our basic, not so basic strategy actually, but process parameters we need to take care of, in-process parameters, welding attributes, welding quality, and then product requirements. So those are our connectors for the different optimization tasks that we look at. And then once we have all of these, we just map it back, so we have control of our process. We use different types of physics in our models: electrical, thermal, acoustic, and mechanical, and we plug those into machine learning algorithms and AI. We have 3 people in the group working on AI and machine learning presently. Will be more. And I want to mention, I have a couple of more minutes here. So in my research group, if you feel like you have something you find interesting in what I've said, then we do machining, laser welding, injection molding, topology optimization, and data-driven analytics and AI. And the research group I'm heading, we have process modeling, data-driven analytics, and experimental validation as 3 cornerstones in our research, and different expertise. And Yeah, I mentioned this before. This is what we strive for. Knowledge-induced and physics-induced algorithms to a next generation development. That's what we want to do. Okay, I think that is that slide. Now, before I leave, or leave the stage actually, I want to show another slide. And it's this one. It's from University of Skövde. Let's see. Yes, it's like that. This one is a national incentive in Sweden. So we got funding from the government of Sweden to develop educational packages for people in industry, experts, let's say beginners level, intermediate level, and expert level. So it's a pyramid of education where we develop courses, specific courses for specific things. Yeah, and we call this WISER, digital transformation and industrial excellence. And it's directed to universities, but also to industry, companies, people who are unemployed, students who want to study extra. The different topics that we have at the university are these. So it's a fair amount of different areas, not only in my area. This area here, I used to be a knowledge owner for virtual machining here. But as you can see, we have information and cybersecurity. We have big data analytics, so real experts on AI, robotics, business intelligence, simulation and optimization, leadership, human in production, integrated product development, virtual commissioning, and Industry 4.0 transformation, and applied AI. So I think for most companies, and I know Roy knows a lot about this, virtual commissioning, what that means is that it means that you make virtual factories and virtual production lines, so you can see how they will operate in real life, even before you create your industry. So if you want more information about this, you contact either me or my Vice President, Dr. Tessin, and you can get some more information, because he is PI for this project. So I thank you very much, and I will end with this slide. Huh? Yeah. That's what it is.
Yes, thank you, Kent, and for showing all the research what's doing just now, actually, in Skövde and in Sweden. And he have demonstrated really advanced research, top of the world, actually. And how to design an electrical vehicle, you have seen that it's not easy. And this afternoon, we are going through little about how to produce it, because doing one is easy, but doing 1 million and be effective and efficient, you need a management strategy for that. So that will be this afternoon. So hope you will join that also.
Okay, ขอบคุณนะครับ ขอบคุณครับ
ค่ะ ตอนนี้ถ้าผู้เข้าอบรมทุกท่านมีคำถามจะถามท่านวิทยากรไหมคะ Do you have any question to ask for our speakers มีไหมเอ่ย Okay, sir. So I got one question from YouTube online, YouTube Live. They asked about the machining. Can you suggest them about what type of cutting tools were used for machining? Yeah.
Hello. Yeah, I would say a type of tool. It really depend on process. So it depend on material you want to use. It depend on how many components you produce. It depend on economy. It depend on tolerance and application area, I should say. So, for example, we work closely to dental company to do implant, and they machine titanium. They machine titanium with very high tolerance. So when you machine titanium, you need special cutting tool and special settings. Then again, if you have people working in Volvo and machine cast iron, it will be a different tool, maybe a little bit cheaper, and because you make a lot. So sorry, I hope we can answer question.
ค่ะท่านวิทยากรก็แจ้งนะคะว่าไอ้ตัวสำหรับตัว cutting tools นะคะก็ขึ้นอยู่กับ type นะคะขึ้นอยู่กับชนิดของ machine นั้นๆนะคะแล้วก็ขึ้นอยู่กับบริบทของเทคโนโลยีในประเทศนั้นๆด้วยนะคะก็อันนี้ก็คือแล้วแต่ depend on situation on technology in these countries นะคะ Thank you for Mr. Solomonson for giving the knowledge Thank you very much ขอบคุณค่ะ
ขอบคุณครับ
ครับท่านใดมีคำถามภาษาไทยได้นะครับ ภาษาไทยได้นะครับเดี๋ยวจะ translate ให้
Thank you. Thank you. My name is Hong Pian. I just want to ask you one question from your experience research, right? You have the two topology for welding, right of welding, pairing together. And the first one you said you have see the wall inside of the first.
Yes.
But I just want to know that how can you know that? How can you know that it have wall inside?
Inside.
Yeah.
You mean
Yeah.
inside?
Yes.
We use a tomograph. It's a 230 kV X-ray tomograph.
Oh.
So we have a system from RX Solutions from France. It's 230 kV, and we can come down to 4.5 micron in resolution of the voxels inside. But that's only if we have only one sample hairpin. But if we look at the complete stator, for example, then resolution will be 80 micron instead. So it depends on size and how close you can come to the radiation source. So when we do a scan, we try to get as good resolution as possible from the scan and the X-rays, and then we take it into software, different types of software. The one we use here is from VG Studio Max. It's because it should be industrially applicable, so they can use it. But in my research group, we use our own code, and maybe it's too difficult for industry to use.
Yeah.
So because we not like to click around, we like to code ourselves.
Yes. Yes. Because it's very difficult to find that wall. That's right.
Yes.
Because in our electrical power, we use like a partial discharge for the check this one for wall inside.
Okay.
That's I wonder why you can find this one.
Yeah.
Because it's very difficult to find that. Thank you
Yeah.
for your answer.
But no problem. Very welcome. We can talk later. Maybe I can explain a little bit more in detail if you like. We can do that.
Thank you.
Yeah.
ถามอีกไหมคะ No questions นะคะสำหรับผู้เข้าอบรมนะคะที่ฟังไม่ทันนะคะสามารถเดี๋ยวหลังจบการอบรมหรือสัมมนาในครั้งนี้นะคะสามารถขอสไลด์ได้ที่สปีกเกอร์แล้วก็ท่านวิทยากรจะส่งสไลด์ให้นะคะลำดับต่อไปนะคะก็จะเป็นการพักรับประทานอาหารกลางวันนะคะเราจะพักกันทั้งหมดประมาณ1ชั่วโมงนะคะแล้วก็เดี๋ยวเราจะกลับมาสัมมนาในเซสชั่นบ่ายกันต่อนะคะตอนนี้มีอาหารกลางวันรออยู่ด้านนอกแล้วนะคะสามารถรับอาหารกลางวันแล้วก็เข้ามาทานด้านในห้องนี้ได้นะคะค่ะขอบคุณค่ะ
ขอบคุณ
thank you
ครับ
very
ขอบ
much
คุณครับเข้าใจครับ
fix what I've broken. Oh, 'cause I need you to see that you are the reason. There goes my hand shaking, and you are the reason. My heart keeps beating. I need you now. If I could turn back the clock, I'd make sure the light defeated the dark. I'd spend every hour of every day keeping you safe. I'd climb every mountain and swim every ocean just to be with you and fix what I've broken. Oh, 'cause I need you to see that you are the reason. I don't wanna hide no more. I don't wanna cry no more. Come back, I need you. You are the reason. Just a little closer. Come a little closer. I need you to hold me tonight. I climb every mountain and swim every ocean just to be with you and fix what I've broken. 'Cause I need you to see that you are the reason.
I found love for me. Darling, just dive right in. Follow my lead. Well, I found a girl, beautiful and sweet. I never knew you were the someone waiting for me. 'Cause we were just kids when we fell in love, not knowing what it was. I will not give you up this time. Darling, just kiss me slow. Your heart is all I own, and in your eyes, you're holding mine. Baby, I'm dancing in the dark with you between my arms, barefoot on the grass, listening to our favorite song. When you said you loved a mess, I whispered underneath my breath, but you heard it. Darling, you look perfect tonight. Well, I found a woman stronger than anyone I know. She shares my dreams. I hope that someday I'll share her home. I found a hollow to carry more than just my secrets, to carry love, to carry children on song. We are still kids, but we're so in love, fighting against all odds. I know we'll be alright with time. Darling, just hold my hand, be my girl, I'll be your man. I sing a few With you between my arms, barefoot on the grass, listening to our favorite song. I have faith in what I see. Now I know I have met an angel in person, and she was perfect. I don't deserve it. You were perfect tonight.
ลาซาด้าเซลใหญ่ครบรอบ 11 ปี ลดได้อีกสูงสุดถึง 6 ต่อ
ยากต้องขับรถไล่ดูทีละโครงการเจ้าเขาแบบนี้ดีอยู่แล้ว เชื่อเขาดิ
มันก็ไม่ได้ยากขนาดนั้นปะแต่ตัวเองไม่จริงจังกับเขา
ไม่ใช่ไม่จริงจัง แต่เรายังไม่พร้อม เชื่อเขาดิ
เราพร้อมก็ไม่ต้องมีแล้วปะบ้านมันผ่อนได้
ทำเรื่องกู้สินเชื่อมันยุ่งยากทำกิจ
When it feels like surgery and it burns like third degree, and you wonder what is it right? When your inside's breaking in and you feel that ache again, and you wonder what's giving birth. If you could let the pain of the past go, of your soul, none of this is in your control. I'm going under, and this time I feel there's no one to save me. This all or nothing really got a way of driving me crazy. I need somebody to hear, somebody to know, somebody to have, somebody to hold. It's easy to say, but it's never the same. I guess I kinda like the way you numbed all the pain, and now the day bleeds into nightfall, and you're not here to get me through it all. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love. I'm going under, and this time I feel there's no one to turn to. This all or nothing way of loving got me sleeping without you. Now I need somebody to know, somebody to hear, somebody to have, just to know how it feels. It's easy to say, but it's never the same. I guess I kinda like the way you help me escape. And now the day bleeds into nightfall, and you're not here to get me through it all. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love, and I try to close my eyes when it hurts. Sometimes I fall into your arms. I'll be safe in your sound till I come back around. But now the day bleeds into nightfall, and you're not here to get me through it all. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love, but now the day bleeds into nightfall, and you're not here to get me through it all. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love.
ลิปพับที่ดีกว่า
ถ้าจะต้องทำงานถึงขนาดนี้เปลี่ยนมาทำงานประจำดีกว่าไหม
หนูชอบงานนี้ค่ะแม่
I'm going under, and this time I feel there's no one to save me. This all or nothing really got a way of driving me crazy. I need somebody to hear, somebody to know, somebody to have, somebody to hold. It's easy to say, but it's never the same. I guess I kinda like the way you numbed all the pain, and now the day bleeds into nightfall, and you're not here to get me through it all. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love. I'm going under, and this time I feel there's no one to turn to. This all or nothing way of loving got me sleeping without you. Now I need somebody to know, somebody to hear, somebody to have, just to know how it feels. It's easy to say, but it's never the same. I guess I kinda like the way you help me escape. Now the day bleeds into nightfall, and you're not here to get me through it all. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love, and I try to close my eyes when it hurts. Sometimes I fall into your arms. I'll be safe in your sound till I come back around. But now the day bleeds into nightfall, and you're not here to get me through it all. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love, but now the day bleeds into nightfall, and you're not here to get me through it all. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love. I let my guard down, and then you pull the rug. I was getting kinda used to being someone you love.
Before we were using Monday.com, our team was drowning at work. Our days used to split between work and managing work, but Monday.com just took care of all of the management, so we could simply focus on the work itself. As soon as
reason for me to change who I used to be. A reason to start over new. And the reason is you. 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 I'm not a perfect person. I never meant to do those things to you. And so I have to say before I go that I just want you to know I found a reason for me to change who I used to be. A reason to start over new. And the reason is you. I found a reason to show a side of me you didn't know. A reason for all that I do. And the reason is you. Tell me something, girl. Are you happy in this modern world? Or do you need more? Is there something else you're searching for? I'm falling. In all the good times I find myself longing for change. And in the bad times I feel myself. Tell me something, boy. I'm too tired trying to fill that void. Or do you need more? Ain't it hard keeping it so hardcore? I'm falling. In all the good times I find myself longing for change. And in the bad times I feel myself. I'm over deep end, watches are diving. I'll never make the ground. Crashed on the surface where they can hurt us. We're far from the shallow now. In the shallow. In the shallow. In the shallow.
got me 10 feet off the ground. Hearing what you say, but I just can't make a sound. They tell me that you mean it, then you go and cut me down. Wait, you tell me that you're sorry, didn't think I'd turn around and say that it's too late to apologize. It's too late. Said it's too late to apologize. It's too late. Yeah. Take another chance, take a fall, take a shot from you. Need you like a heart needs to beat, it's not from you. Yeah, yeah, I loved you with the fire red, and I was turning blue. And you said, sorry like the angel, heaven let me think was you. But I'm afraid it's too late to apologize. It's too late. Said it's too late to apologize. It's too late. Yeah, yeah. Too late to apologize. Too late. Too late to apologize. Too late. Said it's too late to apologize. It's too late. Said it's too late to apologize. It's too late. Said it's too late to apologize. Yeah. It's too late to apologize. Yeah. Holding on a rope got me 10 feet off ground. It's been a long day without you, my friend. And I'll tell you all about it when I see you again. We come a long way from where we began. Oh, I'll tell you all about it when I see you again. When I see you again. Who knew all the pains we flew, the things we've been through, that I'd be standing right here talking to you about another path. I know you love to hit the road and laugh, but something told me that it wouldn't last. I had to switch up, look at things different, see a bigger picture. Those were the days, hard work forever pays, but now I see you in a better place. Yeah. And how can we not talk about family when family's all that we got? Everything I went through, you were standing there by my side, and now you gon' be with me for the last ride. It's been a long day without you, my friend, and I'll tell you all about it when I see you again. We come a long way from where we began. Oh, I'll tell you all about it when I see you again. Oh, 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 first you both go out your way in the vibe. It's feeling stronger with small. Turns to a friendship, a friendship turns to a bond. And that bond will never be broken, that love will never get lost. And when brotherhood comes first, and that line will never be crossed. Established it on our own, and that line had to be drawn. And that line is what we reach, so remember me when I'm gone. Ooh, and how can we not talk about family when family's all that we got? Everything I went through, you were standing there by my side. And now you're gonna be with me for the last ride. So let the light guide your way. And hold every memory as you go. And every road you take will always lead you home. Oh, it's been a long day without you, my friend. And I'll tell you all about it when I see you again. We come a long way without you, my friend. Oh, I'll tell you all about it when I see you again. When I see you again. When I see you again, when I see you again.
Yelling at the sky, screaming at the world. Baby, why'd you go away? I'm still your girl. Holding on too tight, head up in the clouds. Heaven only knows where you are now. How do I love again? How do I trust again? I stay up all night, tell myself I'm alright. Baby, you're just hard to see this. I put the record on, wait till I hear a song. Every night I'm dancing with you. Every night I'm dancing with you. Never got the chance to say your last goodbye. Gotta move on, but it hurts to try. How do I love again? How do I trust again? I stay up all night, tell myself I'm alright. Baby, you're just harder to see this. I put the record on, wait till I hear a song. Every night I'm dancing with your ghost. Every night I'm dancing with your ghost. How do I love again? How do I trust again? I stay up all night, tell myself I'm alright. Baby, you're just hard to see things. I put the record on, wait till I hear a song. Every night I'm dancing with your ghost. Every night I'm dancing
Well, you only need the light when it's burning low. Only miss the sun when it starts to snow. Only know you love her when you let her go. Only know you've been high when you're feeling low. Only hate the road when you're missing home. Only know you love her when you let her go. And you let her go. Staring at the bottom of your glass, hoping one day you'll make a dream last. Dreams come slow, they go so fast. You see it when you close your eyes. Maybe one day you'll understand why everything you touch surely dies. But you only need the light when it's burning low. Only miss the sun when it starts to snow. Only know you love her when you let her go. Only know you've been high when you're feeling low. Only hate the road when you're missing home. Only know you love her when you let her go. Staring at the ceiling in the dark, same old empty feeling in your heart. 'Cause love comes slow, it goes so fast. Well, you see it when you fall asleep, never to touch it, never to keep. 'Cause you loved it too much, you dived too deep. But you only need the light when it's burning low. Only miss the sun when it starts to snow. Only know you love her when you let her go. Only know you've been high when you're feeling low. Only hate the road when you're missing home. Only know you love her when you let her go. But you only need the light when it's burning low. Only miss the sun when it starts to snow. Only know you love her when you let her go. Only know you've been high when you're feeling low. Only hate the road when you're missing home. Only know you love her when you let her go. Well, you only need the light when it's burning low. Only miss the sun when it starts to snow. Only know you love her when you let her go. Only know you've been high when you're feeling low. Only hate the road when you're missing home. Only know you love her when you let her go. And you let her go.
บ่นบ่อย เดี๋ยวลูกก็ว่าเราไม่เข้าใจเจนอัลฟา
ส่งอย่างแบดอีกแล้วเรา
แบบนี้ค่อยเหมือนหน่อย
เปิดใจให้เขาเรียนรู้และเป็นตัวเองไปพร้อมกับโกโก้ครันช์มื้อเช้าที่อร่อย มีประโยชน์ได้ทุกวัน
ขอบคุณ Oh, with her. Here's to the ones that we got. Cheers to the wish you were here, but you're not. Let's drink, bring back all the memories of everything we've been through. Toast to the ones for today. Toast to the ones that we lost on the way. 'Cause the drink bring back all the memories and the can reach out a call you, but I know I will one day. Yeah. Everybody hurts sometimes, everybody hurts someday. Yeah. But everything gon' be alright. Gonna raise a glass and say, yeah. Here's to the ones that we got. Cheers to the wish you were here, but you're not. 'Cause the drinks bring back all the memories of everything we've been through. Toast to the ones here today. Toast to the ones that we lost on the way. 'Cause the drinks bring back all the memories. And the memories bring back you. Memories bring back you. There's a time that I remember when I never felt so low. When I felt alone, the hatred was too powerful to stop. Now my heart feel like an effort, and it's lighting on the dark. I'll carry these darkest for you, that you know I'll never drop. Hey. Everybody hurts sometimes, everybody hurts someday. Yeah. But everything will be alright. Gonna raise a glass and say, yeah. Cheers to the ones that we got. Cheers to the wish you were here, but you're not. 'Cause the drinks bring back all the memories of everything we've been through. Toast to the ones here today. Toast to the ones that we lost on the way. 'Cause the drinks bring back all the memories, and the memories bring back you.
โฟโมสโอเมก้า369มีสารอาหารเสริมพัฒนาการสำคัญเพียบลองเลยโปเกมอนเทรดดิ้งการ์ดเกม
They say, oh my God, I see the way you shine. Take your hand, my days are placing both in mine. You know you stopped me dead when I was passing by. And now I beg to see you dance just one more time. Ooh, I see you every time. And oh my, I like your style. You make me wanna cry. And now I beg to see you dance just one more time. So I say, dance for me, dance for me, dance for me, oh. Never seen anybody do the things you do before. They say, move for me, move for me, move for me, hey. When you're done, I'll make you do it all again. I said, oh my God, I see you walking by. Take my hand, my dears, and look me in my eyes. Just like a monkey, I've been dancing my whole life. You just beg to see me dance just one more time. Ooh, I see you every time. And oh my, I like your style. You make me wanna cry. And now I beg to see you dance just one more time. So I say, dance for me, dance for me, dance for me, oh. I've never seen anybody do the things you do before. They say, move for me, move for me, move for me, hey. When you're done, I'll make you do it all again. They say, dance for me, dance for me, dance for me, oh. I've never seen anybody do the things you do before. They say, move for me, move for me, move for me, make you do it all again. No, 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 yeah. They say dance for me, dance for me, dance for me, oh, oh, oh. I've never seen anybody do the things you do before. They say move for me, move for me, move for me, yeah, ooh, ooh. When you're done, I'll make you do it all again. They say dance for me, dance for me, dance for me, oh, ooh, ooh. I've never seen anybody do the things you do before. They say move for me, move for me, move for me, yeah, ooh, ooh. When you're done, I'll make you do it all again, all again. I love it when you call me señorita. I wish I could pretend I didn't but every touch is your love. It's your love. Ooh, I should be running. Ooh, you keep me coming for you. Right in Miami, thought I was up for summer when sweet tip of me before I even knew her name. La la la. Feel like oh la la la, yeah, no. Sapphire moonlight, we dance for hours in the sun. Feel the sunlight, her body feel right in my hands. La la la. Feel like oh la la la, yes. I love it when you call me señorita. I wish I could pretend I didn't need ya, but every touch is your love. It's your love. Ooh, I should be
lunch. It's breathing a lot, and so maybe after 1 hour, will I have a break after 1 hour? I can. It's okay.
Okay. And after that, you continue or not?
Yeah.
Oh, okay.
Yeah. So how long time can I? 6 p.m.
Oh, about 3. We can ask you.
Yeah.
About 3. Okay.
3 okay. Okay. I'm joking.
Passing is so long. So long.
Ja, det kan man spela på.
Ja, men det behöver inte. Därför att... Change your plans. Vi sa runt universitetet. 5 skulle vi äta middag. Men allting som du får.
Ja, jag tänker det är bra att 95% av vårt personal har det riktigt.
Får de 3 till dig nu eller? Ja. Man är inte med i samma.
What do you think is necessary? Okay. Yeah.
ค่ะขอต้อนรับนะคะผู้เข้าอบรมอีกครั้งนะคะสำหรับการบรรยายในช่วงบ่ายนี้นะคะค่ะการบรรยายช่วงบ่ายนี้นะคะจะเป็นการบรรยายในหัวข้อ How to make manufacturing industry resilient นะคะโดย Professor Dr. Roy Anderson ค่ะซึ่งเป็น Associate Dean International Affairs Department of Industrial Engineering and Management จาก School of Engineering Jönköping University Sweden ค่ะ For afternoon lectures, it will be a lecture on the topic of how to make manufacturing industry resilient by Professor Dr. Roy Anderson. He is an Associate Dean, International Affairs Department of Industrial Engineering and Management from School of Engineering, Jönköping University, Sweden. Please welcome Dr. Anderson on the stage.
Thank you so much. Really happy to be here and distribute my knowledge to you, and I hope you will have a great afternoon and learn a lot. My purpose here is a little also about to explain for you TQM, Total Quality Management, what is lean production, what is Six Sigma, and the company today, the big international company especially, using a combination of them. And they do it because they need to be resilient. But when I say resilient, what I'm meaning, that I'm also going to explain for you. And also we are going to discuss supply chain, logistics, and how important it is to be robust and flexible in the future market to be successful. And also, we discuss that Kent will start and how to design a vehicle and so on. But also now we are going to discuss this afternoon how to do it and what kind of strategy should we have. Because the demand of vehicle will be enormous in the future for electrical vehicle. So we must try to producing maybe 1 million cars a year at least. And how to do that? First, from the business world, you have all this index, and you have some proof here. The disturbance have increased the last year. Maybe you can see this pattern. So vulnerability of the supply chain, the company is increased the last year and will be even more increased in the future. So how it comes depends on many things. For example, Kent show all these metals, and they is located around the world in different places. And that makes also it's difficult because supply chain will be wider and broader, and maybe even more in the future. Other drivers for this is that we try to centralize our stored product and distribution channels because it's more effective and efficient to have it in one place. Before, for example, if you think about distribution channels in Thailand, maybe it was 10 places. Now it's 1 or 2 only. We have also a trend to outsourcing. And if we outsource, it takes longer time to get the products. We will also reduce suppliers, going from 3 suppliers to only 1 or 2. That could be a problem also, because what happens if these suppliers get bankrupt or is located in a place that is a catastrophe or something? We have more demanding customers, and they will be more and more demanding. And the 2 here belongs to the lean production. Lean production will take away inventory. And what happens if you take away inventory? If something happens? Here in Thailand, for example, in Bangkok, you have a lot of traffic jam, and you need the products in order to assemble it. So safety stock have been too less in some company. And also this just-in-time practice. That is some of the reason for it's so complicated to operate today. It could look like this in the supply chain, and here is often the focal company. And in the focal company you have different departments that must talk to each other, communicate. How is it in companies? Are they communicate all the time so they will be transparent? No. And you have also first supplier, second supplier, sometimes third supplier. And after the focal company, if you have assembly there, for example, you have customer and you have also end customer. How to manage this? It's not easy. For example, in order to do a processor, every part there, in average, if you take all the parts and how long is the distance that we produce or transport, it could be 1 time around the world or 2 times in total. And how to manage this? It's not easy. And if you're outsourcing a lot of product, it will be even more difficult. Here is one example of a Boeing. The focal company here producing or assembly these parts. And you can see at that picture, they are coming from different countries around the world. And what happens if you have some disturbance in some country? It's not easy to deliver it. What happened in Japan for some years ago? It was a tsunami, for example. And suddenly it was a lot of disturbance in every product. What happened here in Thailand, 2011? Flooding. What are you good to producing here? Hard drivers, for example. Suddenly, no company, Dell, Macintosh, etc., could not deliver computer because of this flooding in Thailand. And it took over 3 months to get new products, new stored hard drivers. So it's really complicated. So companies today must think about how to get a resilient company and supply chain. So supply chain are vulnerable. They need to be resilient. But how to be resilient is the question. How to be resilient? It's not easy. I like this citation from Charles Darwin. It's not the strongest of species that survive, nor the most intelligent, but the most responsive to change. Could we translate that to companies? Yeah, maybe. So what is resilient? So we are going to start with a definition. And it's coming from material science, for example. The ability of material to recover its original shape, follow a deformation. For example, if you have a bean here, you put the load, it's going down. When you take away this load, what happens? It should go to the same place as before, but it will not do that. It will be some little millimeters lower. So can we translate this to the company? Because here you have a definition of resilience. And some authors have done that. But if you look at a dictionary, it's the ability of a system to return to its original state or move to a new, more desirable state after being disturbed. For example, customer can maybe change the pattern. Should you go back to the normal position? No, maybe you must find a new direction. Here is Sheffy that have done much research in this field, because you must also include speed here. So the ability and speed at which the company can return to their normal performance level follow a disruption. But this is not complete. So I have actually, in my PhD thesis, written a new one. So here I also include ability and speed, which the company, organization, and supply chain can return to their normal performance level, follow a disruption, or move to a new, more desirable state. So how can we translate this to the company, and how should they work? But first, we must look also here. It's a new research area, and I have some proof for that. So it's need more research, and it's not easy to have a model strategy that create company resilient. Here we must do some research together, actually. So first, I have some questions to you, and I would you to be a little involved in this discussion. So what kind of risk can be present in Thailand that can impact the company today and in the future? So we are going to discuss a little here, and I will place you in groups. And in groups you will discuss this. And you are going to, one in the group will be a leader and come up with some risk, for example. And you can do it in Thai, because we have a translator here also. So 1, 2, 3, 4, 5. You sit in the, you can sit over there, okay? 1, 2, 3, 4, 5, 6, 7. It's a big group, okay? And here we have a master students. How many of you is master students? Yeah, 1, 2, 3, 4. You can sit together, okay? And you 4, okay? So 5 to 10 minutes, and write it down. So it will be 4 groups. If someone, yeah, yeah. Okay, who is the leader here? One leader that represent all. Yeah, Okay, you are leader? No. You are leader, okay. So you manage your group. Who is the leader here? Your leader? Who's the leader here? You? Okay. Who is the leader here? Who is the leader? You? Yeah. Oh, lady? You're a leader. Okay, good. Leader.
Can you example for the kind of
It could be traffic jam.
traffic jam?
It could be flooding. It can be political issues. It could be, many things.
The kind of which
Yeah. You understand the question? Yeah. For example, traffic jam is one. Yeah, it could be that. It could be that the salary here increasing. Yeah. Yeah, that could be a risk. Yeah. So how the big international company, they look at this risk, what risk we have in Thailand. So think about that. What risk do we have here? Yeah. I will say something that is good to think about. This task here, these questions, is often that the big international company actually see Thailand as a country, as a whole country. Should we producing something in Thailand or should we select Vietnam instead? What risk do you have here in Thailand?
Talking about the list compare between Thailand and Vietnam, why the owner produce some product in Thailand or produce in Vietnam, compare between which country is better, compare between the advantage and disadvantage between two countries.
Two minutes. Would you like to take in English or Thai?
Is English is okay?
Yeah. Would you like to present in English or Thai? Or only short presentation? Thai or English?
Thai and English.
Yeah. It's up to you. Would you like to talk English or Thai?
English.
English. In English or Thai?
I try to explain in English. Don't worry. Speak one.
Yeah. Okay, we are going to have more group work, so we will not solve all the problem in this group today. So let's see what you have come up with. So we start with this group here. Okay.
Thank you very much for the question. What kind of vulnerable risk can be present in Thailand that can impact company? For the first is salary employer, because if salary between income and outcome cannot balance, it will have effect to the employer in the company, because the high property in the company is a human to operate the work. And another one is I think about the water flood, because this is sometimes we cannot control, and water flood will be have effect to the traffic jam. Usually in the case of traffic jam, we can manage by the going to work early. But if water flood is very difficult to make a plan. Yes, something like that in our case. Thank you very much.
Thank you. Thank you. So let's see what you are coming up with here.
Okay. About my group, and we will talk about the Thailand of Impact company. On my team consider and summarize all of the impact company, such as the first one, the part of the company import part from the international or other country, such as China and internal of in the Thailand. But this part maybe change. Okay, and the next of the problem in the impact of company is the policy of government, because of I not believe my president. Okay, okay. The next choice is a competition of the other company, both other country or in Thailand. Okay, and next about the cost of the component or device is changed on time. Okay, and we talk about in my group the technical skill of the labor is one choice in the impact of the company, and the changing of technology is really important, because in the Thailand the technology input from the other company or other country. Okay, okay. So,
Thank you. This group, do we have something new to contribute? Take only the new.
ความเสี่ยงที่ส่งผลกระทบต่อบริษัทในประเทศไทยครับได้แก่ politics ครับการเมืองครับ transportation system ระบบการขนส่ง static of the generation cost of living technology education ด้านการศึกษานะครับ quality of life คุณภาพชีวิต knowledge ความรู้ Thank you.
Something more you would like to contribute?
Okay. Could I sit down? Stand up. For our group, as we talk about the risk of the company, something. In Thailand, for example, we compare between Thailand and ASEAN, for example, Vietnam, and the first one, the risk in country, the first one, policy. For the policy, we think about the policy. We think about the government policy first. That is important thing. If the government don't have exactly the way the direction to for the country, so the policy very important for the list of company to continue to keep going the product. And the second one, we think about geometry first, because the geometry, for example, the transportation or the logistic or something, is easier to ship the product worldwide. The third one, human. Yeah, human. Yeah. If you don't have the man force, the labor or the people to force to the company to cannot keep going, cannot continue until finish. Thank you.
Thank you. Thank you. Thank you. Really good, all the groups here. And but what do you think it's the most important when the international company look at where should we producing? Of course, it's different aspects. And education of people, of course, it's really important. Transportation and logistics in the company is also in company and country. It's really important. Salary, is that important? Yeah, but not the most important actually. The values a country have is also important. Political system, if it's stable, is important. If there is any natural catastrophe that can happen, it's important. But it's many aspects. And you pick all of them actually. So really good. So let's see, which company is resilient today? And which company is the biggest, largest today? We are going through history here. Here is the biggest company, largest company, 1955, 70 years ago. What kind of company can you see here? A lot of vehicle company producing product. You have a lot of oil companies here. But it's belong actually to the vehicle sector. Are you agree? General Motors, steel in order to producing something. So it's production company here. And vehicle, most of them. Okay, let's see what's happened now. 1992. Can you see some differences here? Yes, of course, but not so much, actually. It's more or less the same company. What is Kodak? Are they resilient? Okay, let's see now. 2002, what can you see here? Actually, more or less the same company. And a lot of US company. Now, close your telephone, close your computer. Now, you will do the list for me, who is the 10 biggest company today? I have it in next slide. So don't search on internet. So discuss 10 biggest company today and write it down. And let's see how many you will pick there. We have a winning group, I think, okay? So it's competition. The 10 biggest company today, you cannot use the telephone or computer now, okay? Okay, 5 minutes. GM, okay, right on. GM. Oh, sorry. No. Ah, but you can see that. Student is very creative. I know that. Not how much. Student is also more creative than teacher.
We mean the 10 company biggest in the world or in Thailand?
Yeah, no,
in the world. In the world.
Yeah, today.
Today.
Yeah, 10. In the world, not Thailand. In the world. Have you list Apple, Boeing? Yeah, write it down so I can see.
Okay.
Write it down so I can see it.
Yeah.
Senaste 20 åren. Det är inte bara en strategi. Inte bara 20 år, bara 10 år. Ja. Hur många är kvar i topp 20 idag? av de 20, hur många är topp 20 idag? Topp 20.
You see our extra workers.
Maybe
เท็กซัสโก ก็คือน้ำมันก็คือ
some
เท็ก
new
ซัสโก
company
รวม
have
กับ
come
เทฟ
in
ลอน
here.
เหมือน
Could be
Exxon
some
Mobil
new company here. Could be some new company. Yeah. Maybe CP Group should be here. I don't know.
We have no idea.
Yeah, no, I don't. Yeah, yeah.
เทสลา
บริษัทอะไรบริษัทอะไร
เทสลา
เทสลา So maybe it's coming in some new company here. Have you considered that? Maybe CP Group coming in here?
around the world
Yeah.
อ๋อที่บริษัทของจีนนิปปอน
Some new company. Yeah. Okay. Yeah. Yeah. Okay, hurry up, hurry up. They are almost finished. They are. So, hurry up, hurry up. So you have your list there. Okay, your group number 3. Okay, your list. List. Okay. You will explain.
อีกเลยนะ
Yeah, your group too.
yeah
Maybe we'll give it back to you, sir. Okay. Okay.
Sorry, can remember. Forgot to. For me, it's group one.
Group 1, yeah.
Okay, thank you.
Okay, you have group 2 there.
Okay.
Okay, hurry. 2 more.
okay just move in
Yeah, 2 more. Okay, let's see now. Which group will win? Let's see. You will have a lot of surprise here. And also, 20 years ago, if you're doing some research in resilient companies, it's really good to look at this list and see how they're working. But look here now. So yeah. How many? This group? Yeah, check. Okay, check. How many? How many? 3. Yeah. And have you how many? 3. Okay. Okay, let's see. Which group is the best group? You have examined which group? Number 2? Yeah. How many? 3 score. You score 3, okay. Is that group? 3, okay. And this group? 4. And 3. So which group? It was that group. So you have 4 actually. So here we have a winning group. Pick 4. It's really good. But could you see a pattern here? Can you see a pattern here? What kind of company today that is the most successful? It's computer-based company, IT. You have one vehicle company there, Tesla. And you have also some financing company here, bank, Visa, for example. And you have also healthcare sector. But if you look at this company today, but first, we have 11 to 20 here. And you can see most of them is from US. But these 10 companies, do you think they are resilient? That means that they will have the same position or better 2030. And look what's happened 2022. Top 10 performance in 2022. So that means out of these, more or less all of them was not doing any profit. last year. For example, Apple, minus 28%. It's a lot. Microsoft also. So what do you think? 2030, 8 years from now, which company will be the biggest? That also, if we had and know it, we could look at how they're working. Because if they will be successful 2030, they will work in a resilient way. And how to do that? How to work in a resilient way? So you still will be top 10. That will I explain for you after the break, coffee break. So 20 minutes. 2:30 we start, and I'm going to try to explain for you how they should work. Okay, coffee break.
Everybody hurts sometimes, everybody hurts someday. But everything will be alright. Here's to the ones that we got. Cheers to the wish you were here, but you're not. 'Cause the strings bring back all the memories. All the ways we go. Toast to the ones of today. Toast to the ones that are lost on the way. 'Cause the drinks bring back all the memories. And the memories bring back you. They say, oh my God, I see the way you shine. Take your hand, but there's a place in both in mine. You know you stopped me dead when I was passing by. And now I beg to see you dance just one more time. Ooh, I see you every time. And oh my, I like your style. You make me wanna cry. And now I beg to see you dance just one more time. So I say, dance for me, dance for me, dance for me, oh. Never seen anybody do the things you do before. They say, move for me, move for me, move for me, When you're done, I'll make you do it all again. I said, oh my God, I see you walking by. Take my hand, but there's a look in my eyes. Just like a monkey, I've been dancing my whole life. You just beg to see me dance just one more time. Ooh, I see you every time. And oh my, I like your side. You make me wanna cry. And now I beg to see you dance just one more time. So I say, dance for me, dance for me, dance for me, oh. Never seen anybody do the things you do before. They say, move for me, move for me, move for me, When you're done, I'll make you do it all again. They say, dance for me, dance for me, dance for me, oh. Never seen anybody do the things you do before. They say, move for me, move for me, move for me, When you're done, I'll make you do it all again. No, yeah. They say, dance for me, dance for me, dance for me, oh. I've never seen anybody do the things you do before. They say, move for me, move for me, move for me, When you're done, I'll make you do it all again. They say, dance for me, dance for me, dance for me, oh. I've never seen anybody do the things you do before. They say, move for me, move for me, move for me, When you're done, I'll make you do it all again, all again. Only when you come missing, you're it down. I wish I could participate in the nature that ever touches your love. It's your love. Oh, it should be running. Oh, you keep me coming for you. And in Miami, thought I was the summer when 60 feet of me.
twist. I was good.
su retro style, modela por las aceras de todos los Shandai, que nunca caduca su belleza absoluta. Para el café de mi inspiración eres tú la azúcar. Dime que sabrás a dulce boca, dame de ese guaguancó, no te hagas la loca. Trae poca ropa, ponte que te toca. Si la vida es un carnaval, tú eres mi garota. Viene como viene, como viene, como va. Tú tienes todo lo que yo quiero y mucho más. Que tus huellas del malecón no hay quien las borre. Esa mi hot baby, oye el Torres.
Half of my heart is in Havana, ooh, na, na. It took me back to East Atlanta, na, na, na. Oh, but my heart is in Havana, my heart is in Havana, Havana, ooh, na, na. Half of my heart is in Havana, ooh, na, na. It took me back to East Atlanta, na, na, na. Oh, but my heart is in Havana, my heart is in Havana, Havana, ooh, na, na.
It's el Torres, mi hot baby. Desde aquí hasta La Habana. That's what I'm talking about.
Havana, ooh, na, na.
I don't wanna know, no, no, no. Who's taking you home, 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 home? Love you so, 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 so. The way I used to love you, no, I don't wanna know, no, no, no. Who's taking you home, 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 home? Love you so, 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 so. The way I used to love you, oh, I don't wanna know. Wasted. The more I drink, the more I think about you. No, I can't take it. Maybe every place I go reminds me of you. Do you think of me, what we used to be? Is it better now that I'm not around? My friends are acting strange, don't bring up your name. Are you happy now? Are you happy now? I don't wanna know, no, no, no. Who's taking you home, 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 home? Love you so, 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 so. The way I used to love you, no, I don't wanna know, no, no, no. Who's taking you home, 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 home? Love you so, 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 so. The way I used to love you, oh, I don't wanna know. Every time I go out, yeah, give it from this one, give it from that one, that you got someone new. Yeah, I say but don't believe it. 'Cause even in my head, you got some in my bed. Maybe I'm just a fool. Do you think of me or we used to be? Is it better now that I'm not around? Things are acting strange. Don't bring up your name. Are you happy now? Are you happy now? I don't wanna know, no, no, no. Who's taking you home, 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 home? Love you so, 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 so. The way I used to love you, no, I don't wanna know, no, no, no. Who's taking you home, 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 home? Love you so, 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 so. The way I
meet you better on your birthday. Do you like this? Do we like this? Do we lay it down where it touch your poop like this? Matter of fact, never mind, will I let the past be? Maybe he's right now, but your body's still me. I don't wanna know, who's taking you home, love you so. The way I used to love you, no, I don't wanna know, who's taking you home, love you so. The way I used to love you, oh, I don't wanna know.
We couldn't turn around till we were upside down. I'll be the bad guy now, but no, I ain't too proud. I couldn't be there, even when I tried. You don't believe it. We do this every time. Seasons change and our love will cold. Leave the pain 'cause we can't let go. Run away, but we're running in circles. Run away, I dare you to do something. I'm waiting on you again, so I don't take the blame. Run away, but we're running in circles. Run away, let go. I got a feeling that it's time to let go. Say so.
Va?
Okay, can we start?
Okay, let's start our next session now.
Okay. Are you ready for session 2? That I'm going through some fundamental in order to create resilient companies. But as you saw before the break, it's not easy for the company and how to operate. And new demand is coming in. A new company. So competition is huge today. But first, I'll try to explain for you what is TQM, what is Lean, and what is Six Sigma. I have a course in Lean production, and it's a 4-credit course. I have also a course in Six Sigma with a project, 5 credit. So now I'm going to explain for you in 1 hour, 9 credit. Could I do that? Yeah, maybe. You are so clever. PhD student and teacher here, so it will be only brief, okay? So what must you focus on? And can't explain before lunch that it's so important with the tolerance. Otherwise you cannot do an electrical vehicle. So you must work with process. And you must work to decrease variation. decrease variation in your processes. Going from this to that one. Is that easy? No, of course not. You must using quality tools. Statistics, process control. You must use design of experiment. You must maybe use simulation, etc. So, if you will be good in quality, it's actually go from a process like this. First, it must be stable, and after that, improved. So variation will be minimized, or as less as it can be. And it was more important when we talk about electric vehicles, when vehicles that some company engines with petrol. So variation monitoring will be even more important in the future. I like this picture. What to do to solve a problem? In order to solve this problem in the fastest way, we do like this. Have you seen that in Thailand? But they do like this? Do you think they have? I've seen that in Sweden. Yes, of course. And I can see it now in this classroom. Where? Look there. Here. It's leaking water here. What to do? The same as in picture. Exact the same. Do you think we have solved the problem now? No, of course not. But in order to solve a problem, we must have a process, we must have a system. Who will take care of that? Should I do it? Should you do it? No, it must be a system. Otherwise, it will be like this. It not disappear. Do you think this will disappear? Tomorrow, maybe it's not coming any water. What do you think? No. And now it's increasing. We must employ some manager that take care of this. But now the clever engineering from your university will solve it like this. Really good engineer. Maybe some of this master student. But what should you do? You must try to find the root cause of the problem. And for that, it's need a system. You need a quality management system and how to working in a good way. For example, this picture is from Volvo. Volvo in Skövde. They have this system and improvement system. Here we have the low level that everyone should come up with an improvement. And it's an easy improvement, just do it improvement. But if it's little more advanced, it's go to this weekly meeting where they discuss problems or opportunity to improve. if it's too advanced or another department also will be involved, it's going to this Kaizen group. And it's people from different departments that come together maybe once a week and discuss how to solve it. And if it's too advanced for this group, it's go to the Six Sigma group. And it's often some people, some staff that is trained to solve problem. So these people are really good in statistics, for example, in simulation and other tools. And you need methods. Here is PDSA or PDCA. Do you know about it? It's how to attack a problem. We have a problem there, for example. The first here is to plan. And here, how to plan for this problem. We must have some tool and ask what the water is coming from and doing some investigation. So here we plan. After we look at it, we'll see if we can do something about it. And if we have solved it, we control so it's not happen again. That is important. And act is the last. It should not even happen in the future. And maybe we have some other issue that is belong to the same problem. That is PDCA. And many companies work with this structure. So even if they are TQM company, Lean company, or Six Sigma, that is the fundamental. How to working with improvement. That is so important today and in the future. We must continuously doing improvement. And what we are doing today, can we do it little better tomorrow? That is a mindset that must be present in companies and also in university, actually. Here is a slide about the improvement or the quality of a product. For example, 100 years ago, the right quality was 0.25. That means if we're producing 4 products, 1 is wrong. It was okay that time. Some years later, we're producing 12 products and 1 was wrong, and that was okay. Six Sigma, we're producing 1 million and 3 is wrong. That was good quality for some products and in some process 20 years ago. And today and in the future, it must be even better. And in order to be that, we must have more method, more knowledge, and so on. And here is also about logistics cost, inventory cost, and cycle time. And you can see that in the slide here. It's a lot of improvements over the year. And if I had 2020 here, it's even better. It's half, actually. So we must continuously improvement. You can see that here. And it's even more important to have a holistic view. And the overview of the whole supply chain. And also when we producing products, that process must go faster and faster. Mechanical typewriter had 30-year life cycle. Word processor have 1 year approximately. What about your telephone? How often are you changing your telephone? Every 3rd year? Some every 2nd year? Some of you maybe every year. How often are they coming out with a new model? Samsung coming up, how often? Very often. iPhone, Apple, how often they come out with new models? Every year, once, but they also come out with different models between. And here we can see a little about the history, what had happened the last 120 years or 100 years. Could we see a pattern here? And I have shown you now, we must continuously improvement, and we must do it faster and faster. Are you with me? You must improve all the time and do it faster and faster. We could see that on the slide. We could also see that before the break. Some company is not resilient. Only 3 or 4 top 20 was still there. And which company will be top 10 in 10 years from now? So what can you see here? Here we have mass production. Ford, 100 years ago, start with mass production. After that, they improve the process, and statistic process control come in, and other methods in order to improve. What happened here, 1960, 1980? Something happened in Japan. Japan that time was really poor, no money, and they producing some product with really bad quality, and they asked for help. They asked Deming and Duran, that was coming from US and teaching the leader in all sectors. And today they're producing products that is the best quality in the world. They were coming in here and come up with TQM, Total Quality Management. And after that, they improve TQM, because in this time, Japanese leader was teaching TQM. And in TQM, you have one fundamental, continuously improvement. So they improve TQM and create Toyota Production System, or Lean. And 1980, suddenly, Japan producing better product than they could do in US and in Europe. What happened with the US people that time, do you think they still buying product from US? Then they could produce better product from Japan. The US people will always have the best. So that means that the car that was producing in US was half the amount 1980. So it was crisis in US. So they start with, we must be better, they think. So they start with Six Sigma, some company, and especially Motorola. And today, Six Sigma and Lean have merged together and have been Lean Six Sigma. And what is Lean and what is Six Sigma? Here, for example, 100 years ago, they producing like this and have this strategy. They time control, break down the work, brain work at the office. So the manager said to the employee how to work. Do you think we have continuously improvement at that time from a worker? No way. We have inspection and so on. And they producing this car. What's the difference to producing this car today and producing that car? Have you seen that car in Bangkok? Yeah, it's a really common car. And Toyota. What's the difference? Could you have this car in red? Red color? No. Only one model. How many different models and different way can you have this Toyota? You can have different engines, different colors, different radio system, different, many. And if you multiply all this, it will be over 100,000 different Toyota Avanti here. Do you think it's different when you're producing the cars here and there? When you're producing, actually it's more or less the same. That have not developed so much. But the circumstances have changed a lot. How many suppliers was involved here? Zero. Only one focal company, no suppliers. How many suppliers here? A lot. What about when we come to risks? Do we have more risk when we produce in that car? Of course. So there we have big differences if you compare 100 years ago. So it's an environment around it. But producing these two cars more or less in the same way today, actually. And here is some research about which car is the best today. And also This is a big research project 15 years ago. It's involved, I think it was 20 researchers. They investigate all the vehicle factories in the world. All. And they find this assembly plant productivity. Japan, in average, it's hours per vehicle, 17. United States, 25. Europe, 35. And the worst factory, 25, and the best. So the variation is less here also. And if we come to defects, the Japan assembly defects per 100 vehicles, the average was 52. It's a lot. But still, they are best. In US, 78, and Europe, 76. So still, Japan is better when it comes to quality. But as I mentioned before, in order to compete, you must think and have a holistic view. Do you think I have a Toyota? No. I will never buy a Toyota because I don't like the design. Some of you that have a Toyota? Yeah. Up with your hand if you have a Toyota. Because today it's many other popular cars. Honda, BMW. I have a BMW. I know it's not the best car, but I like it. And if we come to inventory profile, so it's the same investigation. So here we have the focal company, vehicle manufacturers here. So here we have Toyota, Volvo, BMW, etc. So here is the factory. Days of inventory. So that means, what this means, days of inventory. It's how many days we can producing and not need any deliver to the factory. So you can see here, days of inventory in the factory. Very good, because it costs money. But what happens if it's a disturbance, a risk? In that case, it's a problem. If we look at inbound logistics, first suppliers. Here, you have a lot of inventory. That costs money. Who will pay for that inventory? The end customer, of course. So the focal company working with lean production, but the supplier must also do it. And they don't do it today so much. Some of them, of course. And you have also here distribution and retail. A lot of inventory. And inventory is so expensive. Lean production. Take rid of this inventory or try to do it. And we could see the focal company, all the vehicle factory working with lean production today. And here is the values that is so important in TQM. So why customer is in the middle? Because of we producing and do business because we have customer. focus on processes, so it gets us a holistic view. Base decision on fact, find the root cause, and improve continuously. And the most important, after customer, let everybody be committed. Everyone. It's the value that Juran and Deming train the Japanese leader. And if you compare with ISO 9000 today, you can see it's more or less TQM. You have customer focused leadership, involvement of people, and so on. More or less the same. So if you see any company that is or had this ISO, you should think it's a TQM company. At least TQM company. But what happened after here? 2020, Lean Six Sigma. We know that we must also be agile. And many things is coming in today. And we could see that from this fortune list about the biggest company. Something happened, and it's happened just now. And we have many different tools and other things that we must consider. CSR, additive manufacturing, AI, digitalization, and producing closer to the market. So what coming next? Should it or its end Lean Six Sigma? No, of course not. Something coming here, and that we must do research. We must investigate company that we know is resilient. If we know which company will be resilient and investigate how they're working, we can come up with a model how we should work in the future. But we have also this to consider, the industrial revolution from specialization to customize products. And here is a good explanation what lean is about. Here, the worker work all the time. So really effective worker here. All of the three is really effective, but not efficient. You know that this costs money. And if you would like to be a lean company, and you can also see here, the process time is 30 minutes, half an hour. That is not good. So you must take rid of the waste. And in Toyota, they recognize 7 waste. But you can see 8 waste here. All this is waste. Waiting is waste, overproduction, inventory waste, transportation is always waste, over quality is waste, and movement. All this is waste. And if it's waste, it costs money. And it gives no value to the customer. And invest, we have said that beginning it was 7 waste, but we include that one. And that one is, if you have a lot of the 7, you cannot thinking about improvement. So therefore, it's another waste. Like this. You take your brain and put it somewhere else, or thinking about all this waste. So, and if you attack all this waste, get rid of them, suddenly you have this process. And what about the lead time? A few seconds, and you do only value adding time here. So in a process, if you're working with lean, you must recognize the value adding time, necessary time, and waste, and improve it. Here is some different if you compare Ford with Toyota. Ford was give order, do that, don't ask, don't improve, do your work as I saying to you to do it. Don't think, don't use your brain. But Toyota or lean production, a learning organization. If you do some mistake, what happened? Nothing, but you should improve it so it not happen again. That's the big difference in the mindset 100 years back in time and now. But the production and how to produce more or less the same. But the mindsets have changed. And it's also in lean production that you must follow up. Someone that like football, soccer, up with your hand if you like soccer. I know that Thai people is crazy in soccer, especially the teams in UK. Manchester United, Liverpool, Arsenal, Chelsea. I know that, but you're a little shy, so you cannot. I am Liverpool fan. How many here is Liverpool fan? Manchester United, Chelsea. You are too shy. Okay, but do you know the most famous Swedes? He's a football player. Do you know any from Sweden more than Kent? And do you know any more? No? Zlatan Ibrahimovic. Everyone knows Zlatan. And if you are, you can compare lean production with soccer actually. You have some principles here. And you have that in lean also. You have values and so on. And you should not think only on yourself, for example. And you have way of working. And you have a trainer, a coach, that said to you that if we do like this, it will be fine. And it's the same in lean. If we're working like this today, it will be fine. What happens if you lose the game? What happens with the result? If you lose, it will be negative. What you do as coach? You analyze the game and you discuss with the player what happened yesterday and so on. What should we do so it's not happen next time? What do you think they do in lean production? Every day they have a daily meeting, short daily meeting, maybe 15 minutes, and discuss the result yesterday and how to working today. And what should we do in the future? 10 minutes. After that, everyone go and working. It's the same as be coach or manager for a football team. And also, takt time is important. We should producing in a certain takt time. For example, it should come out 200 cars today. And at the end of the day, we are producing 200 cars. What happens if we're producing 201? Is that good? No, it's not good. Something had happened if you're producing more. And we should not do that. But we can have a variation, 200 plus minus. And if it's within this boundary, it's good. And here you have the values in lean production. Can you compare them with TQM? Customer focus, do we have that in TQM? Yes. Do you have continuous improvement? Yes. Do you have involvement, teamwork? Involve everyone? Yes. Do you have this? Working with process is the same? Yes. Quality in all stages? Yeah, more or less. The new one is this just in time. But it's more or less TQM, but some improvements. How would you look like? Of course, this is the best. Many companies that was using lean production in Europe, Sweden, they was like this. They take rid of too much stored product. So they were in risk. So I would like to say that this, if you use lean in the wrong way, you will be like this. If you use lean in a good way, you use lean and also Six Sigma, you will be like this. Here is a typical TQM organization. Typical TQM. And this man, I think it's man, I think he's happy. Yeah. But if something happens, it's not so healthy. So, of course, it's better to be fit. And in order to be like this, you must use a combination of lean and Six Sigma, actually. So therefore, what is Six Sigma? Do you know now what is lean? Do you know what is TQM? I hope you have a little clue. Now, Six Sigma is coming. So here is a definition from, actually from Ericsson, the company Ericsson. Focus on reduce cost of poor quality, customer that is not happy, using a systematic proving methodology, PDCA, and focus of variation reduction. What happened? Here is the fundamental in and the framework of Six Sigma. You have a top management commitment, but what is new is that you have a training. You have training from an employee and all employees, and you have this in the middle. It's a DMIC, more or less the same as PDCA improvement. But you have also a measurement system that measuring cost of poor quality. And you have more stakeholders involvement, and you do improvement by project that gives result. This is Six Sigma. And I tried to explain PDCA for you before, and this is Six Sigma PDCA. Define the project, but you have more tools and more statistical tools in Six Sigma. Yeah. So as you can see here, in define the first phase, you have many tools that you can use. And that means also that you must train the people. So you train the people in tools and method in order to improve. You focus on cost of poor quality, and you focus on reduce variation. That is the fundamental in Six Sigma. Okay, approximately 10 minutes left. Okay, if you compare TQM, Lean, and Six Sigma, in TQM you often have this kind of tools, FMEA, histogram, benchmarking, and so on. And if you implement Lean, you have little more tools that you include beside the tools in the middle. And it's more analytical tools, actually. And if you introduce Six Sigma in your company, you introduce even this kind of tools, and you need statistics. You need knowledge in variation. You need knowledge in simulation. You need knowledge in design of experiment, for example. So if it comes to the focus, Six Sigma, compare, Six Sigma is red, Lean is green, TQM is blue. Six Sigma focus more on cost when Lean and TQM. Oh. Speed is important, and Lean, as you can see there, focus more on speed than TQM and Lean, Six Sigma. And here is one article that I have producing, and it's different than similarities. And I will not go through that now. But this movie is really good explanation what's the difference. And it's 5 minutes. Okay.
Imagine you're the manager of a supermarket chain. You've noticed that two things need your immediate attention. The first issue is how to handle the different kinds of waste that you encounter at your supermarket. The next one requires you to address the supply chain issues at the supermarket, which are causing delays to the morning delivery of milk, leading to customer dissatisfaction and attrition. These problems can be solved by incorporating two of the most popular quality management methodologies in the world, Lean and Six Sigma. One famous for its ability to handle waste, and another known for process improvement. But what if there was a methodology that combined the concepts of both Six Sigma and Lean? One that could solve all your issues? Well, there is, Lean Six Sigma. Before we dive into Lean Six Sigma, let's take a closer look at its parent methodologies. First off, Lean is a methodology that focuses on providing value to the customer, eliminating waste, continuous improvement, reducing cycle time. Lean and Six Sigma both aim to handle waste. But what is this waste? Waste is any step or action in the process that a user does not gain any value from. In short, things that users wouldn't want to pay for. Why would a consumer want to pay extra for the additional truck that was required to deliver milk to the supermarket just because the other one broke down? This waste can be divided into 8 categories. Let's have a look at each of them. 1. Transportation. This waste refers to the excess movement of people, tools, inventory, equipment, and other components of a process than it is required. 2. Inventory. This waste occurs due to having more products and materials than required. This can cause damage and defects to products or materials, greater time for completion, inefficient allocation of capital, and so on. 3. Motion. This refers to the time and effort wasted due to unnecessary movement of people, equipment, or machinery. This could be sitting through inventory, double data entry, and so on. 4. Waiting. This can be time wasted waiting on information, instructions, materials, or equipment. 5. Overproduction. This is the waste created due to producing more products than required. 6. Overprocessing. It refers to more work, more components or more steps in a product or service than required. 7. Defects. This is the waste originating from a product or service that fails to meet customer expectations. 8. Skills. This waste refers to the waste of human potential, underutilizing capabilities, and delegating tasks to people with inadequate training. For years now, many systems have emerged that use the lean methodology to identify and handle the different kinds of waste. Some of the more popular and effective ones are JIT, or just in time, 5S, and Kanban. The JIT methodology focuses on reducing the amount of time the production system takes to provide an output, and the response time from suppliers to customers. 5S is another methodology that focuses on cleanliness in organization while improving profits and efficiency. Kanban is also another popular methodology to achieve lean. It is a visual method to manage tasks and workflows. Kanban enables users visualize the workflow to identify issues in the process and fix them. These methodologies help in optimizing the waste production and are often used together to maximize results. So that's the first problem solved. Now, let's have a look at how you can improve the supermarket supply chain efficiency. For that, let's have a look at the other part of Lean Six Sigma, Six Sigma. Six Sigma is a set of tools and techniques that are used for process improvement and removing defects. Let's see how Six Sigma makes that possible. Six Sigma has two major methodologies, DMAIC and DMADV. You can learn more about these two methodologies by checking out our Six Sigma in 9 minutes video by clicking on the top right corner. Let's have a closer look at DMAIC, since Lean Six Sigma uses the DMAIC methodology of Six Sigma. DMAIC is an acronym for Define, Measure, Analyze, Improve, Control. It is used to improve existing products and processes so that it can meet the customer's requirements. In the Define phase, you determine what the goals of the project are. In this case, you want to reduce the amount of time taken to deliver milk from the warehouse to the supermarket, so that it is stocked on the supermarket shelves before 8:30 in the morning. In the Measure phase, you measure the performance of the current unaltered process. The milk truck leaves at 7:30 a.m. in the morning and can take one of 3 routes, A, B, and C. Route A is currently the preferred one, as it takes only 60 minutes to reach the supermarket, compared to the routes B and C, which take 70 and 80 minutes respectively. In the Analyze phase, you find out why the defects exist. Since routes B and C were school bus routes, by reducing the starting time by 1 hour at 6:30 instead of 7:30 meant avoiding the traffic. Routes B and C now take 40 to 45 minutes to reach the supermarket. Route A still takes the milk truck 1 hour to get to the supermarket, even when the truck leaves at 6:30 a.m. In the Improve phase, performance can be improved by addressing and eliminating the root causes. Now that you've realized that advancing the milk pickup by an hour and changing the route to Route B can save time, you change the process accordingly, providing your workers with ample time to stock the milk into the shelves before the morning rush. And finally, in the Control phase, you make regular adjustments to control new processes and future performance. You continue to monitor the delivery times and try out alternate routes to continually improve the process and ensure even faster delivery. This process change led to reduced man hours and cost, enhanced sales, and customer retention. The Lean Six Sigma methodology offers many such benefits to businesses. Let's take a look at some of them. 1. Increase in profits. 2. Standardized and simplified process. 3. Reduced errors. 4. Employee development. 5. Value to customers. And that is Lean Six Sigma for you. Now, before we're done,
Yes, that was one example about these two concepts. I have 2 slides more to show you.
In my research, 2010, I was investigate how to create resilient companies. And I come up with 4 things or values that must be fulfilled. And that is, you need to have a Lean Six Sigma strategy, but also working with supply chain and other companies. So the focal company should strive to be agile, flexible, robust, and that Lean Six Sigma helping you. You must be design and innovation led, because suddenly it's coming some product that is better than I can produce or design. You must collaborate and be integrated, led in the whole supply chain. And see your supplier as friends and also customer, actually. You need to have a risk management culture in the whole supply chain. These 4 I was coming up with after I was doing more research and come up with one more important, and that is create common values and culture, not only in their own company, but also in the whole supply chain, and not growing too fast. What happens if you're growing too fast? You cannot create common value and culture. Toyota had really problem 10 years ago because they was growing too fast. Today they know that we cannot grow too fast because we must have the same values. If the company working like this, the output will be, what can you see here? My definition of resilient. Do you think I have right? We don't know. But we need more research. And we need more research, for example, if a company in Thailand using a combination of Lean Six Sigma, what will the output be? So it needs more research. So when it comes in disturbance, if you're working like this and have a Lean Six Sigma strategy, you will be resilient. Hopefully. The professor have always right, or professor have always right sometimes, not all the time. Okay, questions? That was my last slide for you, and here, working with this concept, the company might be resilient and will be the world leader 2013. Maybe. You never know. Questions?
questions มีคำถามไหมคะ มีไหมเอ่ย Okay sir I got one question from YouTube live he asked about TQM he said like we are talking about that is same like TQM total quality management or not sir and what is it difference
TQM with the other concept was?
Yes, as we talking, it's same like TQM is total quality management or not?
Yeah, it's total quality management. Yeah, but also that if a company is a new, maybe 50 employees, should they start with Six Sigma? What do you think? Or should they start with Lean or TQM? Actually, the answer for that is you should start with TQM. After a while, you realize we need something more. And in that case, they can go from Lean or Six Sigma. I have done research. The company that going from TQM to Six Sigma, and you can do that. And you can also do opposite, TQM to Lean. But TQM will be fundamental there. After a while, when you are working with TQM and Lean, you realize we need something more. And then the company realized that it's a way to introduce Six Sigma. And the opposite, if you have Six Sigma and TQM, after a while you realize we need Lean. It's often like this. Yes?
Yeah, Roy. It's working? Hello? Roy, how can all of these researchers, how can they implement Lean Six Sigma in their experiments that they do? If they do experiments, can they use Six Sigma quality implementation for experimental work?
Actually, I have many students that ask me, could you help me because I would like to use the D-mic in Six Sigma when I do my thesis work, because it's a really structured way. So of course you can implement some method from Lean and some method from Six Sigma to use it in an isolated way. Of course you can do that. Was that the question?
Okay any more questions มีคำถามอื่นอีกไหมคะ Okay if don't have any question thank you very much for Dr. Anderson thank you very much
Thank you thank you
Yes ค่ะและลำดับต่อไปนะคะขอเรียนเชิญหัวหน้าโครงการนะคะท่านผู้ช่วยศาสตราจารย์ดร.ฤทธิชัยเผ่าเนียมกล่าวสรุปโครงการและกล่าวขอบคุณท่านวิทยากรที่ให้เกียรติมาบรรยายและให้ความรู้สำหรับอบรมเชิงปฏิบัติการระดับบัณฑิตศึกษาในหัวข้อความท้าทายประเทศไทยก้าวกระโดดสู่ผู้นำระบบการผลิต e-drive components และ manufacturing resilience ค่ะขอเรียนเชิญค่ะ
ครับนะครับกล่าวนะครับจนถึงนะครับช่วงเวลานี้นะครับอินไทส์ช่วงเวลานี้ก็ขอบพระคุณทุกท่านนะครับท่านวิทยากรนะครับแล้วก็คณาจารย์คณะกรรมการนะครับแล้วก็ผู้เข้าร่วมอบรมทุกท่านนะครับในหลักสูตรปริญญาโทนะครับแล้วก็ปริญญาเอกนะครับจากตั้งแต่เช้าถึงนะครับถึงเวลานี้นะครับเราได้รับความรู้จากท่านวิทยากรนะครับ แต่ละท่านเนี่ยนะครับอย่างสูงเลยนะครับในการที่จะนำ knowledge หรือว่าความรู้แล้วก็มุมมองต่างๆนะครับให้เราสามารถที่จะพัฒนานะครับแล้วก็คิดอีกก้าวอีกสเต็ปหนึ่งนะครับโดยเฉพาะเรื่องเกี่ยวกับช่วงเช้านะครับของดร.เคนเกี่ยวกับเรื่องของ e-drive components นะครับก็จะเห็นว่ามีหลายนะครับหลายประเด็นนะครับในเรื่องของการทำ research นะครับแล้วก็เรื่องของงานวิจัยแล้วก็ในอนาคตนะครับก็สามารถที่จะร่วม cooperation ระหว่างกันได้นะครับในขณะที่ช่วงบ่ายนะครับเราก็ได้เจอท่านดร.รอยนะครับในการที่จะให้แนวคิดนะครับแล้วก็หลัก management ต่างๆนะครับให้สามารถประยุกต์ใช้ในองค์กรแล้วก็ในการศึกษาของเราต่อไปได้นะครับนี่ก็เป็นนะครับสเต็ปเริ่มแรกนะครับที่จะพัฒนาระดับบัณฑิตศึกษาของเราครับก็นะครับในที่นี้ก็ขอกราบนะครับขอบพระคุณท่านวิทยากรแล้วก็คณะกรรมการผู้ร่วมงานต่างๆนะครับขอบคุณมากครับ
Okay, so let me translate in shortly. He said that we are really appreciate. Thank you for our speakers and participants here. Since the morning session until now, we have got many knowledge from all of you guys, and we will improve. We will bring this knowledge and improve ourselves and can use it in our future life, and hope to have cooperation between two countries in the future. Thank you. และลำดับต่อไปนะคะเดี๋ยวขออนุญาตเรียนเชิญผู้ช่วยศาสตราจารย์ดร.ฤทธิชัยเผ่าเนียมนะคะมอบของที่ระลึกให้แก่ท่านวิทยากรด้วยนะคะ Next please invite Assistant Professor Dr. ฤทธิชัยเผ่าเนียม to give the souvenir for the speaker. Please welcome. ขอเรียนเชิญนะคะ First speaker Mr. Peter Beer ค่ะSecond, please welcome Professor Dr. Ken Salomonson. And next, please welcome Professor Dr. Roy Anderson. And the last one, please welcome Mr. Tersin Aslam, Vice President, University of Hervey. ค่ะและโอกาสสุดท้ายนี้นะคะขอบคุณทุกท่านนะคะสำหรับการเข้าร่วมสัมมนาในครั้งนี้และหวังว่างานวันนี้นะคะจะให้ความรู้ความเข้าใจและข้อมูลที่เป็นประโยชน์ในอนาคตได้ค่ะ Thank you for your participation. I hope today's seminar has given you knowledge, insight, and information which can be used in the practical manner. Thank you very much. นะคะลำดับต่อไปนะคะเดี๋ยวขอเชิญถ่ายรูปร่วมกันนะคะบนเวทีค่ะขอเรียนเชิญทุกท่านเลยค่ะ May I invite all speakers to take a photo together? On the stage. ค่ะขอบคุณทุกท่านนะคะ แล้วหวังว่าเราจะได้พบกันอีกครั้งในโอกาสต่อไปนะคะ ขอบคุณค่ะ